Good morning. My name is Valeria Sieira. I'm a postdoc at CA in Paris-Saclay in France. And well, I want to present this work today, which is a work in progress that we are doing with with Antoine Stugaret, who is my supervisor, and several colleagues from different projects, for example, Storm Genesis and Whole Sun Collaboration. So the idea of this project is within this bigger project, which is called Storm Genesis. And the idea of this is to explain and characterize the solar eruptions from the very beginning, from their initiation until its propagation through the heliosphere. So I will be working mainly in these two parts. So the eruption, the onset eruption, and also the particle acceleration and the propagation of the eruption. So how are we, the idea to do this is, of course, to understand the physics behind the eruption and also to improve our modeling. So this is a numerical framework. It can be used for any active region. So we just need to have an initial magnetogram and extrapolation that we want to use, and that's it. Then the MHD simulation start to work. So for this, we are using the Pluto code, which is very well known in the community of solar physics. This is a very open, it's very well established, it's friendly code, it's open source, and we are using full MHD, where we use the magnetic field from the magnetograms in the photosphere together with extrapolation. We are also considering some thermal conduction and radiative cooling. And also is non-ideal MHD. That means that we consider also magnetic diffusivity. For the part of the particles, this is already implemented in the code. So the way that is done is with the test particles. And that means that there is no feedback on the MHD. And is using guiding center approximation, which is very good approximation in the cases that we have a very strong magnetic field. But today I'm not going to talk about this part because this is still under analysis. So I'm going to focus on the MHD simulations. So this is, we are going to analyze this active region in particular. So this is a very big active region, which is close to the central meridian. And of course, it has an eruption, it has a flare, and then we can see the eruption. So this active region for this same event was already analyzed before by other authors that they describe the process of the eruption as a two-stage ribbon component. So here in this work of Yoshi et al., we can see the magnetogram associated with this active region, and we can see the first stage is the formation of the flux rope above this above the polarity inversion line, and we can see the rising of this flux rope and the formation of these parallel ribbons, which are pointed with this arrow. And after that, the eruption continues rising until it reaches the point of a magnetic 3D null point, which triggers the reconnection, and then we can see this quasi-circular ribbon. So here in this work, they also determine the velocity of this eruption, which we can see here that it has also two phases, the slow phase and accelerated phase. So the first phase is around like 50 kilometers per second, and then the other phase is around 160 kilometers. So there is also a previous numerical study done by Abhijit Prasad and collaborators, which is also a Whole Sun collaborator, which is, he did an isothermal and incompressible simulation, MHD. That means that there is no evolution of these thermodynamical variables, together with the norms for free extrapolation. So that means that initially we have a non-zero initial Lorentz force at the beginning. And it's very strong, especially at the lower atmosphere. So together with this, they conclude in their work that the eruption is triggered by this imbalance of the Lorentz force, because the Lorentz force start to squash the field lines. Then this drives a reconnection. We start to have an increase of the current density that we can see here in color. And after this, we have the eruption. So in our work, is a very similar approach, because we are going to use exactly the same active region and the same extrapolation. So this is the magnetogram again, and this is a cut along this plane. So to have an idea how the magnetic field looks like. And then we use a stratified atmosphere. We can see here the temperature that goes to from 10 to the 4 to 10 to the 6 Kelvin. And then, well, we see here the density and the gas pressure. And this atmosphere is plane parallel. So, and I put here between quotes the photosphere, and we are considering photosphere and chromosphere because it's not completely true, because we are assuming that it's fully ionized, so there is no neutrals here. Well, together with the transition region and the corona. And this atmosphere is in equilibrium, but it's hydrostatic equilibrium. So the Lorentz, the part of the magnetic field is not in equilibrium. And well, these are some technicalities of the numerical simulation. We use a certain resistivity. At the bottom, we use line-time boundary conditions. That means that we have no motions at the bottom. And the question that we ask is, in this configuration, if we can have an eruption, or if this additional thermodynamical evolution has important effects. And also, how is this energy that we have, the energy release that we have, how much of this energy is transformed into thermal and non-thermal emission? So this is a movie of the simulation. I just want to clarify that there is no flux rope here imposed in the simulation. It's just the magnetogram and the plane parallel atmosphere. We just run the simulation. At the beginning, we have a little bit of the settling down. Then we have a mass loading there, and then the rising phase. So this is density, and this is the temperature. So of course, we say, okay, what triggered this eruption? And what is the role of the different forces that are playing here? So to do this, we wanted to isolate the flux rope, but of course, in this configuration is very complicated because we don't have, since we don't impose the structure of the flux rope, is very complicated and very messy magnetic field. So we, with the help of this tracking algorithm that was developed by one of the collaborators, that is Andreas Wagner, and the use of one of the quantities, for example, in our case, we use the twist, which is the current density along the magnetic field line. In one plane, he was able to track the flux rope with this quantity. So here you can see in this color, the twist, the red is positive and the blue is negative. And here in the contours, we can see the identification and the tracking of the flux rope in time. So at the very beginning, it doesn't work very well because it's not very clear in this plane. Of course, the flux rope is moving, is not always in the same plane. So if you pick a plane, you probably won't see the entire, very well, the entire evolution of the flux rope. But this is mostly the plane where the flux rope remains after a certain time. So here, this is how it looks like, the twist in a 3D plot. And the magenta field lines are the lines corresponding to this contour, to this identification. So with this, once we isolate the flux rope, we can analyze the forces that are acting here. So for the first part, we identify the mass loading. We can see here, this is the Lorentz force in the plane. And this is a sum of one of the field lines of the flux rope. And we can see that there is a very strong component upwards of the Lorentz force. So this upward Lorentz force is loading the mass into the flux rope. So here in this movie, this is the density along the field line, and you see that the bump of the density is propagating a long time. So with this, I think we can say that the mass is really loading into the flux rope. So this is a plot with different times of the mass loading. So we can see here the initial mass loading, and then this mass is propagated until it reaches the apex, and then continues the evolution continues. So here, and also this is an HF alpha image, and we can see that the mass loading is produced in the location where in observations we have a real filament. So this was like a very big surprise for us because it was a coincidence. And so, and then for the rising phase, we see that the flux rope so the mass is loaded into the flux rope, and then it continues rising. And we see that here, for example, we have the flux rope field lines, and in this plane is the Lorentz force. Also, red is positive, so is the Z component of the Lorentz force. So the red part is positive, so upwards, and the blue part is downwards. So we see that always there is a big patch of upward Lorentz force. So we say, okay, maybe we can calculate to prove that is the Lorentz force responsible of this rising. We can calculate the Lorentz force around this flux rope. So here, the solid contour is a flux rope, and the dashed contour is the envelope of the flux rope, and we calculate the average Lorentz force inside that contour. So outside of the flux rope, but in the surroundings. And we can see here, so in this plot, that this line is the Lorentz force, the black one is the total force, and this one are all the non-magnetic forces. That means the gravity, the gradient pressure, and the advection force. So we conclude with this, that the vertical Lorentz force from the surrounding of the flux rope is responsible of this rise. And we could also determine these kinematic properties, and this is the velocity that we approach. But of course, we are still lacking this accelerating phase. So, and this is my last slide. So the good thing of this kind of simulations is that we can calculate observables that we can compare straightforward with the observations. So this is the synthetic emission in 171 from IAA in different planes. So actually in observation, we can only see these planes because we don't have observation from stereo. And these are the side planes. So, and we can see that in the synthetic images, we also have a nice eruption. So to conclude, so our simulation is in agreement with the previous work of Abhijit Prasad in the sense that the Lorentz force is the trigger of the eruption, but in a different way. Oops. And also we found that we have the formation of the flux rope that is self-consistent, and that we have two phases, the mass loading and the rising phase, and both of them are caused by the Lorentz force, but acting in different parts. And also, well, what I just said, that the thermodynamic evolution provides these observables that we can compare with the observations. So what I'm still doing now is to calculate the soft X-ray emission, and also with the addition of the test particle, we are going to be able to localize the sites of particle acceleration and calculate the hard X-ray emission. And of course, we are still need to quantify the energy that is going into these two emission, this kind of emission. So that's all. Thank you very much.
So thank you, and we have time for questions. Yeah, first.
Hello. Yeah, I guess it's on.
Yeah, it's on.
Okay, yeah, thank you. Nice talk. So the Lorentz force drives the mass onto the filament field, I guess. So now you're saying that this is fully ionized in what you started with, but in reality, of course, it wouldn't be that ionized. So have you thought about the differences if you had a realistic ionization compared to what you?
That's a good question. No, I haven't think about this. How can it change with this assumption? But maybe if we consider neutrals, for example, I think we also need to consider another kind of mechanism acting in the chromosphere, like the ambipolar diffusion, for example.
There was another question. Yeah.
Thank you.
Thank you for the good presentation. So
I think so.
I can switch to that.
Thank you.
Thank you for good presentation. From the observational side, can you clarify your requirements to magnetic field measurements? Because you say, oh, we just need the magnetogram. It's hard for us to justify what instruments we need to build, how to continue that. Do you need line of sight, vector, cadence? Do you need Doppler velocity with this? All of that will be useful.
So in this case, we use a line of sight magnetogram. And the cadence is not very important in our case because we don't use several magnetograms. It's just the one, and thank you for this because I haven't mentioned, but we use a magnetogram that is very close from the onset of the flare. So the configuration in the bottom doesn't change much. So for the cadence is okay, but I think which is important is the resolution of the spatial resolution of the magnetogram.
Yeah, thank you. Just for the future, I think it's important to bring these questions as requirements because, again, how we can argue for the instruments if you don't really know some of these details.
Of course, if we have measurements of the magnetic field upper in the atmosphere, that would be the best.
Yeah, that's another important
because we don't have to assume some kind of extrapolation for the magnetic field. But I know that it's very hard, but that would be the idea.
Thank you very much.
Thank you.
Thank you again, Valeria. And we go with the, yep. We go with our next speaker, Devo Ioti Kansabanik, with measuring magnetic field of coronal mass ejection in corona and inner heliosphere using wide field of view spectropolarimetric radio imaging.
Good morning, everyone. So I'm Devojyoti. Today I'll be speaking about how to measure the magnetic fields using of the CMEs, both in the corona and also in the inner heliosphere using radio observations, and why particularly the wide field of view radio imaging observations are necessary. So we all know that why the magnetic field is important for CME because it's plays important role from its eruption stage during the propagation and evolution of its geometry and so on. And not only that, it's when it arrives at the Earth, it's the geoeffectiveness also determined by the vector magnetic field. Now, there are several challenges why these magnetic field measurements are challenging because the plasma of the CME, when it propagates out from the sun, becomes tenuous, and also the magnetic field becomes weaker. And most of the emissions, most of the wavelength are not that sensitive to the small magnetic fields. And there are in situ observations that can provide the localized magnetic field measurements. But as we know that for the large scale magnetic field measurements, that in situ observations are not sufficient. So we need remote sensing observations to get the global information of that large scale structure. And so not only, but the remote observations always either provide you the line of sight magnetic field or the plane of sky component of the magnetic field. But ultimately, for the geo-effectiveness, we need the vector magnetic field. So not only the observations, also we need the better modeling of to constrain the models using the observations to ultimately finding the vector magnetic field from constrained by the observations. So why the radio observations are particularly special for this case? Because radio band is extremely sensitive to the magnetic fields, all kinds of radio emissions. So there are at the coronal heights, the CME produce different types of direct radio emissions, which we can use for the magnetic field measurements. So for example, we can use different kinds of solar radio bursts, which are mostly related to the CME shocks, like type 2 radio bursts and so on. But the CME plasma, the flux rope, and the prominence, the CME core also provide emit direct radio emissions like the thermal free emission or gyrosynchrotron emission produced by the electrons gyrating in the magnetic field. But as we move away from the corona, these magnetic fields becomes weaker, and the electron density also becomes smaller. So the emission frequency becomes too low that it is obscured by the ionosphere, our ionosphere. So we cannot use the ground-based observations. And also this emission strength becomes too fainter to be detected by the space-based radio instruments. But in the as we move away in the inner heliosphere, we can use some indirect techniques, radio observations, for which we can use the background radio sources. And when the radio emissions from these background radio sources are passing through the CME plasma, their polarization properties and their intensity properties are also changed. And these are also very sensitive to the plasma and magnetic field of the CME. So there are several methods, like the very well-known method of interplanetary scintillation that have been used for decades. But for the magnetic field measurements, one can use the Faraday rotation observations that I will talk in the later part of my talk, that we can use to measure the line of sight magnetic field of a CME, of the CME plasma. Now, particularly the radio, overall the full radio wave band, particularly the megahertz and the gigahertz frequencies are preferable for this kind of observations in the coronal domain and the inner heliospheric domain. So in this talk, I will be talking particularly about the, in the coronal domain, I will be particularly talking about the gyrosynchrotron emission, and in the inner heliosphere, how we can use the Faraday rotation measurements and what is the current status of that work. So the gyrosynchrotron emission from the CME plasma was first detected in 2001 by Tim Bastian using the Nancy radio heliograph. And that you can see in this figure, this blob-like structure is the gyrosynchrotron emission from a CME plasma. But due to the instrumental limitations, there are only a handful of studies from the 2001 which actually could detect this magnetic field, detect this gyrosynchrotron emission from the CME plasma and use that for the magnetic field measurements. Now, why it is most challenging? Because this is very faint emissions, about 100 to 1,000 times fainter than the white sun radio emission. And in the radio band, one cannot use a coronagraph to block the white disk. So what we need a very high dynamic range image such that both the white sun and this faint emissions can be detected simultaneously. And not only that, if we want to use this emission to measure the magnetic field, we need the spectroscopic observation. So having detection only at a single frequency is not sufficient. So that we have shown that all the previous observations have very small number of spectral sampling. So when they are estimating the magnetic field, they have to assume several, they have to consider several assumptions. Now, this scenario has been changing over the last few decades using this instrument called Murchison Wide Field Array in Western Australia. It is a square kilometer array precursor instrument. And also we have developed a state-of-the-art calibration and imaging algorithm to make a very high dynamic range images using this instrument. And this is now allowing us to detect this gyrosynchrotron emission from the CME routinely. So there are two examples I am showing for this one. This is one of the CME where we have detected the radio emission from the gyrosynchrotron radio emission from the CME. The background is the white light coronagraph images, and the contour shows the radio emission from the white light structure. And similarly, this is another event where we have detected radio emission from this northwestern CME. And also there is a faint CME structure propagating in the southwestern direction. And we detected a radio emission just behind the leading edge. And so now this instrument now providing us almost routine measurements of the routine detection of these emissions. But the main challenge towards shifted towards the modeling. Because this gyrosynchrotron emission has about 10 free parameters, and most of them there are several degeneracies in these parameters, and one of the crucial degeneracy that we are particularly concerned about is the magnetic field strength and the angle, line of sight angle with the magnetic field. Now, one way to break this degeneracy is the polarimetric measurements that was not available during early generation instruments. But now we have, with the MWA, we can do the polarimetry as well, and we have detected polarization signature from the southwestern CME that I shown here. And what this allows us, so for example, the top panel shows the Stokes I, that is total intensity spectrum, and for the bottom panel, we are showing the Stokes V upper limit. So even we have not detected, but we can put a very strong upper limit because of the precise calibration. And even with these strong upper limits, what we can see in this posterior distribution of the parameters, that it can actually constrain better when compared to only using the Stokes size spectrum. And it breaks some of the degeneracies between the line of sight angle and the magnetic field strength. So this is the main takeaway point from this work is that now the detection of intergyrosynchrotron emission from the CME plasma is now possible. And the Stokes V spectrum is essential for the robust estimation of the magnetic field and the other plasma parameters using this method. Now I'm moving to the from the coronal regime to the heliospheric regime. Now, just going into the details, I just want to give a brief overview what is the Faraday rotation. So Faraday rotation is just when a polarized emission passing through a plasma, magnetized plasma column, its polarization angle gets rotated. And this rotation is proportional to the wavelength square and multiplied by a constant term, which is proportional to the line of sight integrated electron density and magnetic field. So this is called the rotation measure. And if we can measure this rotation, estimate the rotation measure, and somehow we can get the electron density measurements, we can get the line of sight integrated magnetic field strength. Now, this method have been used previously using the instrument called Jansky Very Large Array at 1 to 2 gigahertz. And this has been successfully used up to the 15 to 20 solar radii. And this instrument is observing at the higher frequency at gigahertz frequency regime and also have the smaller field of view. So this cannot cover the entire CME at a single observations, at a single pointing. So they have to, what they did is that so in this panel, I have shown one CME when it is propagating, and there are multiple background radio sources. And they have to point on these different radio sources at some certain cadence to measure the line of sight magnetic field along that particular line of sight. And the main assumption in this method is that during the observations, when you are changing the pointings about 4 to 6 hours, you have to assume the CME structure or CME magnetic field has not evolved, which is not always the case. So that scenario can be changed if we have a wide field of view instrument that covers the larger part of the CME at a single pointing. And that will give you the multiple line of sight measurements using a single pointing. So that we are now going to do using the instrument called the Murchison Wide Field Array. So, sorry. So this left-hand image shows the sun at the center. And due to the high dynamic range image, we can also see the background radio sources, which are mainly just white dots in this figure. And so this will allow us to measure a large, and this is the MWA field of view, this cyan circle. And it will allow us to observe the 60 solar radii region at a single go. So we don't need to point different sources at different over 4 to 6 hours of observations. So, and the left panel is actually showing one of the observations when we keep the sun out of the field of view, and so that we can point much higher heliocentric distance from the sun to measure the magnetic fields at much higher coronal height, higher heliocentric heights, about 110 solar radii. So there is another very important aspect of this MWA observations. Because of this particularly designing, it can easily detect the diffuse galactic background emission which is coming from our galaxy, which is a synchrotron emission and extremely linearly polarized. So the advantage of this emission is that instead of the discrete point sources in the field of view, this is a diffuse emission. So it will give you a spatially continuous Faraday rotation map that is ultimately giving a spatially continuous magnetic field measurements. So, but this is very challenging because of this diffuse emission structure. But this is really possible using the MWA observations, which is most of the radio instruments don't pick up. So not only the MWA, there are several other instruments like the LOFAR, SCAP at the higher frequencies are also well suited for producing these snapshot heliospheric Faraday rotation maps. And we are now working towards doing this using combining all these instruments together, like MWA, LOFAR, SCAP, and also using the MeerKAT. Because combining all these instruments have different capabilities, but one of the big challenge is that all of these instruments are not solar dedicated instruments. So the big first thing we are now developing is that the triggered observing capability for these instruments. So for the MWA, we have recently made it operational that when a CME happened using the near real-time white light catalogs like Cactus or SEEDS, we triggered the MWA observations to observe that particular part of the sky in which direction the CME is moving. So that is now giving us almost capturing the capability of capturing all the CMEs that is happening. And after that, there are several other things we are now doing. That is one of these things is the instrumental calibration, but the major challenge is the ionosphere, because ionosphere is also producing some Faraday rotation contribution, which is in the similar order of magnitude what CME will contribute. So we need to separate them both. Otherwise, the measurement will be wrong. So at the end, what we are trying to, once these measurements will be available, we want to use this for modeling the observations, the observations to estimate the vector magnetic field to constrain the different flux from models. So with that, I will stop here and happy to take any questions. Thank you.
Thank you. There are questions, please.
Lovely talk. Very difficult measurements to make. So commendable that you've been able to do what you have been able to do. The first part of your talk, where you're talking about gyrosynchrotron measurements, relies on a good measurement of the Stokes V. How well calibrated is MWA to make those measurements accurately?
Yeah, right. So the accuracy of the Stokes V polarization not Stokes V, the total polarization, all the polarization components is now about 1% residual leakage. So we can say that whatever we measure is about 1% error bar on the measurement. So that is the accuracy we have achieved.
Well, you're doing better than we are in LOFAR, because we have worked on that and really struggled to make good measurements. So that is good to hear. The second part of your talk just reminds me that we need a solar MWA or we need a solar LOFAR in order to make those kind of measurements. But have you any even tentative data where you're measuring, line of sight magnetic field for CMEs going through your field of view? Or did I miss that in your talk?
Right. So there are some measurements we have because no dedicated observations have been done till date, but we found some archival data from the MWA observations and we used that. So that will allow like only a 5-minute snapshot observations, like, okay, we can measure some changes. Now that I am not using because that is not kind of really, because you need a time series to see it is really the changes due to the CME, when the CME propagating through that line of sight, but it is only a single observation. So it is not that easy to say. So that is why I'm not using that for now.
Yeah, excellent stuff. Thank you.
Yeah, please.
What is the relation of gyrosynchrotron CME with CME observed in white light?
Okay, so it is very hard to answer because this is gyrosynchrotron emission is a non-thermal emission. It is coming particularly from the mildly relativistic electrons, which is gyrating in the magnetic field. On the other hand, the white light is particularly coming from the Thomson scattered emission from the total electron density. So in general, when there is a high-speed CME, we generally expect that there is shocks and also the some internal magnetic reconnections, which can produce these non-thermal electrons in the large number. So we expect larger, stronger gyrosynchrotron emission. But it is, you cannot say that it is a one-to-one correlation. So this is hard to say that this is a one-to-one correlation.
What is the typical energy range of those electrons effectively in your gyrosynchrotron emission?
So, yeah.
Solar flares, we often talk about the MEV electrons, but do you need such high energy electrons?
So, generally the range is about 10 kV to the 1 MeV.
So like
region.
type 2 emitting electrons.
Not that fast you need, but 10 kV to 1 MeV electrons are fine.
Okay.
Yeah.
So thank you again. Yeah, thank you. We go with our next speaker, Nadeep Panesar, the magnetic origin of solar campfires, solar orbiter SDO observations. And you have the time. This is for the going slide. Yes. Just forward. There is no need to backward. Over back. Yeah. And there you have the time. The big one. Yeah. This is for the slide, right? Yeah, I think this is the point. Yeah.
Oh, okay. Good morning, everyone. I'm going to talk about the triggering mechanism of solar campfires. Campfires are small-scale coronal brightenings that were first reported by Bergsman et al. Using solar orbiters EUI data. This is an example of. Oh, thanks. This is an example of a campfire. They are mostly rooted at the edges of chromospheric network boundaries, and their height lies between 1,000 and 5,000 kilometers above the photosphere. In this work, the formation mechanism of campfires and their connection to the photospheric magnetic field was not known. So the work that I'm going to show you today, we investigate the magnetic origin of solar campfires. So what we did, we examined the magnetic field evolution at the base of solar campfires and investigate what triggers these small-scale heating events. For that purpose, we randomly selected 52 campfires in an on-disk EUI images. And then we located the same campfires, the EUI campfires in the AIA images, and studied their line-of-sight magnetic field using HMI magnetograms. We used data from 2 days. One is from 20th May and the other from 30th May 2020. The instrument was in commissioning phase for both days. And this diagram shows the location of solar orbiter and SDO. So they were both looking at the roughly solar disk center. On 20th May, we had about 1 hour of data at every 10-second of cadence. And this is the field of view that solar orbiter's UI observed on that day. Okay, this is the zoom in field of view, the same one. It shows some of the visible campfires at this time frame. And this is the AIA 171. You can see, for example, this campfire appears here, this one here, and so on. And this is a campfire that I'm going to show you in detail. This is a campfire structure in EUI 174 image. And the same campfire you can also see in the AIA 171 and also in AIA 193. Interestingly, when we looked into detail using AIA images, we found that there is a cool plasma structure present at the base of the campfire before it shows up in the images. For example, here, so what happens here, when this dark structure, or you can say cool plasma structure rises, a brightening appears underneath it, this brightening, and it turns into a campfire type structure. The brightening grows with time as the cool plasma structure expands with height. This is the line of sight magnetic field for this campfire. The cool plasma structure is rooted above this neutral line between the opposite polarity flux patches over here. When we followed these flux patches with time, we noticed that they clearly converge towards the neutral line and cancel with each other. Let's see the movie for this same event. Here is the EUI movie, and this is the rise of the cool plasma structure here, this one, and the brightening appears underneath it, turning into a campfire type structure. Similar behavior you can also see in the AIA channels, 171, 304, and so on. This is the, yeah, just follow them. I can't forward these movies now. And this is the HMI magnetograms shows the evolution of these two flux patches which are involved in this campfire event. The average length and width of this cool plasma structure is also similar to the average width and length of the pre-jet mini filaments. To see the magnetic flux evolution quantitatively, we measured the positive flux at the base of the campfire. And here is the plot of positive flux plot versus time. We can see that there is a continuous drop in the flux, and campfire happens at this time, which is an evidence of flux cancellation at the base of the campfire. Actually, with the help of AIA data, because we have longer time data AIA, so we noticed that there were two campfires from the same neutral line, and they both occur at the flux cancellation neutral line. This is the other one. Further, this is time distance map, HMI time distance map that displays a clear flux convergence and cancellation that leads to this event. Here is the time of the campfire. And once the polarity is gone, the negative here, we did not see any further campfires from this neutral line. So overall, 79% of campfires are preceded by cool plasma structures similar to mini filaments in coronal jets. Most of the campfires reside above magnetic neutral lines, and 77% of them appear at visible magnetic flux cancellation sites. However, some of the smallest campfires come from the site where magnetic flux elements were barely discernible. Since I'm comparing these cool plasma structures with pre-jet mini filaments, I would like to show you very quickly an example of a quiet region jet. So this is a pre-jet region here. We can see that there is a mini filament present, this one at the jet-based region. So what happens here when the mini filament erupts, a brightening appears underneath it where the filament was rooted prior to the eruption. This is known as jet-based brightening. It is due to magnetic reconnection here, this one. And then you have a jet here. But in case of campfires, it appears that they occur in the compact loops. That's why you do not see any ejection, or you can say eruptive, even like in this case, we have this jet spire that going outward. And we know that coronal jets occur along open field lines. So this is the difference I can say between campfires and coronal jet. But this brightening that appears where the reconnection happened, it is at the same location. This is the magnetic field for the coronal jet here, and these two patches are clearly converging and canceling. You can also see from this is also evident from this flux plot and this from flux time distance map. Okay. We find many campfires to have a complex structure, but most of them resembles with small scale. Most of them appear as jet-like, dot-like, and loop-like. And these jet-like, loop-like, and dot-like campfires are somewhat similar to the earlier observations of HI-C 2.1. Okay, this is just a plot that shows average lengths, widths, and duration of the campfires. Now, very quickly, I will show you an example of jet-like campfire here. So this is an example of jet-like campfire in EUA 171. So you can see that there is an extension, so we call them jet-like campfire. It is not compact like the previous example. Oh, this is a movie. Okay, so here you can see it's okay, in this case, similar to the loop-like campfire, we also observed cool plasma structure, this one, that clearly rises and leads to this campfire type event from this neutral line where there was a visible evidence of flux cancellation. This is an example of a complex campfire. Here is the campfire, and here is the ejection of cool plasma structure you can see in 304 and 171. This campfire occurs at the edge of a magnetic flux lane, negative flux lane, where there was where the opposite flux was barely visible in this case. Our results support the simulation of campfires by Chan et al., where they show the evidence of magnetic flux drop in 1 out of the 7 campfires. Our observations show the presence of cool plasma structure is much more common than inferred in the simulations, in their simulations. Okay, this is the movie of the same event. We also computed the EM distribution of these campfires. The campfires appear at coronal temperatures from 0.5 to 2.5 million kelvins. And these results are consistent with the findings of Bergman et al. They also found that campfires appear at similar temperatures in their DEM analysis. Okay, in this work, we investigate the dynamics of fine-scale jets and study their magnetic field evolution. So this is an example of fine-scale jet with a bright jet base and a narrow spire. And the AIA images again shows there is a mini filament present in the jet base region, this one over here. So when this mini filament erupts, the jet base brightening appears underneath it. If you remember the example of coronal jet that I showed you earlier, so this is very much similar to that, but this is here we are looking at very fine scale structure, fine scale coronal jet. So when we take a cut across the mini filament here, so we see that the mini filament, when the mini filament rises, the brightening appears underneath it. This is very much similar to typical coronal jet and also the typical solar filaments. So what happens in solar filaments when the filaments erupt, you see a flared arcade that appears at the neutral line. But in case of coronal jets, either the typical ones or the small scale ones, we see a brightening, the jet-based brightening that appears at this neutral line where the filament was routed prior to the eruption. So this is the neutral line for this mini filament and coronal jet. And when you follow these two patches, and you can see there is clear flux convergence and cancellation going on that leads to this eruption. The observed length and width of these jet spires are similar to the HI-C fine scale jetlets that we observed in the past. Okay, this is another example of fine scale jet similar to the previous one. The main difference here is that we did not see the evidence of cool plasma in this one. When we do something here at the jet base region, but when you follow in the movies or make a map, the dark structure, which looks like a mini filament, it does not erupt, and nor the jet-based brightening appears at the location from where it erupts. So we are not sure what's going on here. And this is the neutral line for this one. This is a chronal jet example from Bifrost simulation. These are iron 9 synthesized images. It shows a bright jet base and narrow jet spire over here. The jet is routed above this neutral line. These are the BZ maps of the same jet base region. And the flux convergence and cancellation between these two flux patches clearly leads to this jet eruption. This is iron 9 Doppler map of the same jet. We observed opposite Doppler shifts, this one, in the jet spire, which are often a signature of untwisting motion of the magnetic field in the jet spire. And this is just show the speeds along the along this black cut over here. That blue shifts reaching up to 35 kilometers per second, and the red ones are peaking at 10 kilometers per second. This is another jet example in the Bifrost simulation, similar to the previous one. And here is the summary of my talk. We examined the magnetic origin of 52 campfires using solar orbiter and STO data. We find that most of the campfires are located above magnetic neutral lines. However, some of the smallest come from the sites where magnetic flux elements were barely visible. Consistent results were later reported by Cahill et al. Using solar orbiter's phi data. Majority of campfires come from sites of magnetic flux cancellation, similar to mini filaments in chronal jets, and 79% of campfires are accompanied by cool plasma structure. And these cool plasma structures are routed above magnetic neutral lines where you do see flux cancellation. Our observations suggest that presence of cool plasma structure, that is magnetic flux ropes, are much more common than previously thought in the solar atmosphere. The campfires contain cool chronal temperatures and possibly are small-scale magnetic reconnection events. A Bifrost simulation shows a picture that is consistent with jet observations in many aspects. However, 3D MHD simulations, more MHD simulations need to be investigated for better clarity. That's all. Thank you.
Thank you very much. We have time for one question, please.
Hi, very nice talk, very clear. You talk about the free magnetic energies, 10 to the 26, 10 to the 27.
Yeah.
How did you estimate that? And also, how does that compare to the thermal energies that are released in a campfire, which you can get from your densities and temperatures and so on?
So for the estimation for magnetic energies, these are the crude estimations. We roughly take what is the magnetic field over here is, I think 20 to 30 Gauss. That's how we got these numbers here.
Okay.
Yeah.
So that's the cancelled magnetic energy.
No, this is the magnetic field that is present at the campfire base before the eruption, when you see a campfire.
Okay. And then
before it gets fully cancelled, that's what I meant to say.
in my mind, what's the energy of a campfire, say from your EUV observations? Is it
You
of
mean
that
from
order?
the EUV observation?
Yeah.
Energies from the EUV
Yeah,
observation?
the thermal energy.
Thermal energy.
Yeah.
Oh, sorry, we did not estimate the
Okay.
thermal energies. Yes.
Okay, it'd be interesting
Just
to
the
see
magnetic. Yeah,
kind of
that's a
the
good
energy
point.
partitioning in these events. Like,
Right,
Gordon
right.
Emsley did this kind of stuff for solar flares. It'd be interesting to do that for campfires. Thank you very much.
Thanks.
Thank you.
Oh,
Jane.
thanks. Okay.
We now have our invited talk for this session, Marianna Corsos, Models for Long-Term and Short-Term Flare Prediction.
Okay, so good morning, everyone. And first of all, I would like to thank for the opportunity for the organizers. I changed a little bit of the title of my talk, but the topic almost the same. So with this presentation, I try to address where are we with the short and the medium-term flare predictions. Why is important this? Because our modern society and our infrastructures actually very vulnerable because of the extreme space weather events. And actually, the interconnection nature of our infrastructures actually means that if a disruption is happening in one sector, that can have amplified impact across the multiple areas. So that's why we need to predict the extreme space weather event, especially the source of it, the large flare and CME eruptions in a well advance. So basically, the problem is the high energetical particles, the high energetic particles and the X-ray radiation can reach the Earth within a couple of minutes. So basically, we don't have enough warning window to prepare ourselves. So that's why we need to predict them or identify their pre-eruptive condition of their source regions. And even the problem is when a large flare occurs, it's very often accompanying with the large CME eruptions. And this is what the previous talk nicely explained. The CME actually can cause a bigger problem than, for example, the flares. So how we can predict them? Based on the historical study, we already know that they are mostly coming from the solar active regions. I need to use to get it. So that's why we try to classify their source region, the solar active region, by different classification schemes, like, for example, the Macintosh classification or the other type of scheme. But all of the scheme is agree on that the most energetic flares and CME actually coming from the most complex active regions. And what does it mean, complex? Actually, during the active region, evolution could lead to the unpredictable and absurd changes in their structure and the surrounding magnetic fields. So an active region actually far from the equilibrium state, which means that they are not stable and also not balanced. And due to the very slight disruption, they immediately can do some suddenly changes, which is lead to us for a flare occurrences. So during the solar cycle, actually the large solar flares, the number in general, they are increasing, and when we getting close to the end of the maximum, these large flares, less flares occur. However, sometimes it's not really true, but however, this is more relating that when the cycle is getting more go to the maximum, then more magnetically complex active region appearing. And as we going down to the end of the cycle, less magnetically complex active region appear. So based on these statistics, we can say that only just 10% of the solar active regions during the solar cycle producing N-class flares, while only just 2% of the solar active region will host an X-class flare. But this DER actually can cause a huge problem. So for the solar flare prediction, we can do basically on two different time scales. One is the medium time scale, and the other one the short time scale. During the medium time scale, we are more we would like to understand the evolution of the solar cycle, and to know that when the most magnetically complex active region will start to appear. And we try to predict them maybe within a week or maybe a month. However, with the short time scale, actually we are more focusing on the individual active regions, where we are using the recent solar observation and trying to see how the individual active regions are developing. And we are usually measuring with different kind of parameters. Like here we can see that there is one active region, which is we can see how it's developing a nice data spot. And also we can measure how the magnetic field structure is becoming more and more complex. So how we start the prediction basically? Our first concept, we are looking for a so-called big, bad, and angry active regions. What does it mean, big? Big, which has a huge magnetic flux. Bad, when basically the magnetic field structure is more tangled, more complex, because this is indicating that more free energy is available, which is waiting for to be released. And also angry, which means that it's rapidly evolving. So for example, if you look at these active region, through the 3 days, it doesn't really change the shape. However, in that active region cases, especially that part, if you can look at it, it's changing almost every half a day, because more flux emerging between the pre-existing fluxes, and this is causing the trouble later on. So currently, our predictions are more probabilistic. So basically, we try to estimate the likelihood of the flare, what type of flare cast we should expect it within a given time frame. And our short time forecast windows are basically changed within a few hours up to a couple of days, typically up to 3 days. But however, the uncertainty of our prediction is changing at both to the end. For example, if our forecast window just a few hours, the uncertainty is coming from the random nature, how the active region magnetic field structure is changing, and also this tiny unobserved scale where the flares is erupting. However, from the longer forecast window, which is, I would say, if we're giving a prediction for the next couple of days, then the problem is the uncertainty of our prediction is coming from how the magnetic field structure is developing through this time period. Because in average, the magnetic field structure is changing within 10 to 24 hours. And how we predict the size of the flare. Practically, at the moment, we just can predict that we will have a major flares, so which means that the M or the X class flare, or we can say that we cannot expect a major flare, so it means that probably it will be a C or A or B class flare. And also, we are not really that way we could say that which major flare will be erupted or non-erupted. So basically, as I showed in the previous slide, most of the major flares are actually accompanying with the CME. However, sometimes maybe the CME cannot erupt, so it will be a confined flare. But this is still ongoing how we could predict them, or different methods try to modeling it by some of the flares accompanying CME or not. So for example, what we are sure, the magnetic free energy is the source of the solar flares. So basically the magnetic free energy is accumulating until a so-called critical point when it's reached. But the question is, when this critical point will be reached? We don't know. This is there we are really suffering still. So for example, here is two active region example. So this active region produced several CMEs and also one X-class flare. While this one is also magnetically complex, but it didn't produce an M or an X-class flare, just the C-class flares. So first of all, we calculated how many free energy they have, and practically it's turned that of the maximum free energy what they have is more than enough to produce large solar eruptions. But only this one produced CMEs and X-class flare, while this one is just produced the C-class flares. So we need further methods to identify which active region is producing large solar eruptions, which one is not. For example, here is one proxy parameter. So based on a previous statistical example, they found that if this parameter is cross the 750 Gauss threshold level, then, which is highlighted with this blue horizontal line, then we could expect a large solar eruption within a couple of hours or within a day. So for example, here you can see that this parameter crossed the threshold level, but just few hours before. And this red one is indicating when the X-class flare occurred. However, look at after the flare period, actually this parameter is increased further up. So it means that I would expect a further large solar eruption, but actually it didn't happen. Why in that case, actually this parameter remained below the threshold level. So when we start to, which active region actually become more suspicious for us, what we have to look at a little bit closer. Of course, which have a delta spot. Because within this delta spot, the positive and the negative polarity are really shrink in a very small place within a one penumbra. So, and these two opposite magnetic fields are actually separated by the so-called polarity inversion line. And along this polarity inversion line, the horizontal gradient actually very high. And in the chromosphere or the lower corona, a so-called filament channel is appearing just above the polarity inversion line, where the plasma starts to fill up this filament channel. And after some nonlinear processes, practically this filament channel becoming the source of the CME. So, but this is still not really solving our problem to predict an upcoming flare with a high accuracy. So that's why we need more parameters. And these parameters are usually derived from the different solar observations, but most of the parameter actually is calculated from the magnetogram observations. And these derived parameters are directly directly physical or linked to the fundamental physical parameters. So basically these parameters just give information about the current state of the active region at a specific moment. So basically these parameters can be useful, but including only limited information about what is the ability of the active region to erupt. And also these predictors usually just give a hint when we can expect the large flares. Maybe it could be within a couple of hours, or maybe it will be happened a couple of days later. So actually here I took, I took two very nice summary tables from Stephanie Yardley and Manolis Georgoulis paper. It was just recently published. It is a kind of roadmap, but they are really nicely summarize our current prediction method. For example, in the upper table, these are just summarizing the solar flare prediction models. You can see that there are lots of them. Actually, in the last 20 years, more than 200 parameters was proposed. So that's why it's not really efficient to discuss them individually. And also there are some flare prediction parameters which also try to give information about which flare will occur with CME or which one is not, or also giving some prediction about the what type of solar energetic particles can be expected. So Manolis and Stephanie practically nicely categorized these parameters in 4 different classes group. One is the physical based, which is typically involving data-driven model constructed from the first principle or the empirical. And you see there are less forecast parameter which is based on the physical approach. However, there are more prediction method which is based on statistical analysis. And basically this method giving kind of a hint about the probabilistic what type of flare class and when it can be occurred based on the statistical correlation between the flaring activity and the solar measurements. And of course, now it's well populated the artificial intelligence. And in this flare forecast area, actually the machine learning and the deep learning method is getting more famous, I would say, or handy. So from the machine learning part, they are giving more probabilistic prediction, while the deep learning method are usually based on the artificial neural network method. But in that case, these type of models just giving kind of a prediction, a binary prediction. So it means that based on the data, it will say there will be a flare or no, but it doesn't give the percentage what we can expect. And of course, as human nature, we like to combine things together. So that's why there is a so-called ensemble category where different predictions method or the predictors are combined together. So, but also there are researchers who like to test these proposed methods, how they are operating, how we can use a real forecast. At the moment when they are testing these more than 200 parameters, usually they found that only just a couple of tens are usable for a prediction purpose, and only just few of them give a high probability. So basically, when they are testing it with a different machine learning or based on different data, they found that no method clearly outperforming the others. However, all the methods actually failed because in what sense? That the prediction method cannot really predict the first flares and the last flares. So it means that we cannot predict what will be the first flare from the active regions and what will be the last flare from the active regions. And also the current method cannot give information about how many flares will be together, which follow each other, or when will be the flare quiet time of the active regions. So there are still huge missing bits, our current prediction methods. So I would say we are still in the baby shoes. So there are plenty of space to develop different prediction method and come up with a really good one. So, and also the other missing parts, I would say when we are developing a method, we usually are using our own data. So it means that when we say our method is nicely performance, of course, because it's based on our data. But what about if someone is testing our method on a totally different data, maybe the performance of our method is not good. So that's why actually it's a kind of missing. There is no common data set where all the prediction method can be tested and can be fairly compare them and give which one is the good one and which one is not really trustable. And also the other interesting part is, but now few people and also me and my collaborators identify that there is basically no routine magnetic field measurements from the lower solar atmosphere. And actually, this is the place where the flares and the CMEs are erupting, not from the photosphere. So why we are still observing the magnetic field from the photosphere? So currently, we extrapolated the magnetic field and of the active region at every moment of time. And after that, we made a horizontal crosscut. So it means that we have a series of magnetic field map at different atmospheric heights. So like if we just would use the photospheric magnetogram series, but now we can calculate the different parameter also 300 kilometer above the photosphere or 700 kilometer above the photosphere or even higher up, depending on where we are making the crosscut. And our direction is that we are applying different predictors at different atmospheric height, and we see that what is the maximum height where the actual parameter is still satisfying their pre-eruptive conditions. And at the moment, we found that if the parameter is satisfying their threshold level below 1 megameter, so between photosphere and 1 megameter, then the active region actually just producing a large solar flares. However, the predictors actually satisfying the threshold level well above 1 megameters, it's turned out these active region actually producing flares and CMEs also. And this is kind of some ways an obvious result because the CMEs are originating from the corona, while the flares more occurring in the lower solar atmosphere. So this is a still ongoing work, but this is the kind of proof that we need magnetic field observations through the lower solar atmosphere to improve our prediction method. But luckily, other researcher also starts to supporting that idea. And I just, for example, I learned that there are some NASA missions which are starting to measure the magnetic field from the lower solar atmosphere. So, and the question is, can we go further a little bit with the prediction, not just within a couple of hours, but for example, a week? So, and this is a kind of medium-term prediction, medium-term flare prediction. We started go in that direction, but of course, other researchers also. So, currently, we try to predict that when the most magnetically complex active regions are appearing during the solar cycle. So there are different dynamo models which can describe or giving back the butterfly diagram. However, the missing part of this medium-term prediction is that the dynamo model cannot really describe what is the longitudinal position where these magnetically complex active regions are appearing. So why I am saying that? Because based on the observation, actually, there are a so-called active longitude. This active longitude usually persists for a couple of Carrington rotations, and it's observational actually proven that along this active longitude, the more magnetically complex active regions are appearing, which are producing a large solar eruptions. So, and there are theoretical models, which was developed by Dikpati and her colleagues, where they say that the nonlinear interaction among the so-called magnetorossby waves, the differential rotation and the toroidal magnetic fields actually generating a location, a more favorable location on a certain latitude and longitude, where the magnetic field likes to emerge more frequently compared to the other locations. So basically, this certain latitude and longitude location are identifying a so-called active nest, and this active nest can persist for a couple of Carrington rotations. So that's why we also started to study, is it really, this is a real thing or not? So practically we took the SOLIS magnetogram data from the photosphere and the chromosphere. And we identified the most populated longitudinal position at every Carrington rotation, where more magnetic flux emerged. So we are plotted here this longitude through the last solar cycle. And you can see that basically the location of this most populated longitude are changing over the time, but however, it's also oscillating. So for example, here the blue line is standing from the most populated longitude at the chromosphere, and the green one is stand for the most populated longitude position at the photosphere. And after that, practically we checked where the major flare are occurring, which longitude position. And this is highlighted by the red line. At time to time is not really overlapping each other, but most of the time, yes. So, and after that, we also check that what is the situation about the favorable latitude. To be honest, before that, I never realized that if I am checking the butterfly diagram, you can see some more denser area in the latitudinal location compared to the other part of the butterfly diagram. And that's why we identify the most populated area of the latitude locations, and on the photosphere and also at the chromosphere. And after that, we also check the location where the M and the X flare like to occur. So basically, if you compare with your eyes these 3 figures, you can see that the distribution are very similar. So it means that it seems to be there are some reality in this active nest theory. So that's why I think it would be very nice if the dynamo people also get into this active longitude and predict the location of the active longitude, because it would be much useful when we will know when the magnetically complex active region will appear. And after that, and for the short-term flare prediction, which is the region what we really have to study from the beginning when the active region starts to emerge. So yeah, this is the same. So as a summary, for the short-term prediction, I personally and also other colleagues are believing that we need magnetic field measurement from the lower solar atmosphere. So that's why our Hungarian Solar Physics Foundation developed that telescope, which currently is still in the testing phase, but already producing line-of-sight magnetogram observations from around 700 kilometers above the photosphere. But we are still planning to further add kind of an instrument which will measure the line-of-sight magnetograms above 1 megameters. And also, I strongly believe that we really need to extend our current prediction method from the photosphere through the lower solar atmosphere to make a big leap in the flare prediction area, because the current studies is showing that the accuracy and even the prediction window can be increased. And in the medium-term prediction, I would say it would be nice to develop those methods which could predict the upcoming magnetic flux emerging and where will be the location. So predict the active nest where these magnetically complex active regions are appearing. And thank you very much. And I think my time is up.
Thank you, Marianne. So questions?
Thanks, Marianne, for a nice overview. My question was, you did not say anything about the polarity informations about these active regions. What I'm referring to is, often the dynamo community refers to something called rogue active regions. Your angry active regions, does it have anything to with those rogue active regions? Because they don't seem to follow the Hell's polarity law. So that's also the sort of, Joyce law scatter, which they account for. So did you try to look at from your database that whether you have such percentage of rogue active regions, which is similar to your angry ones?
Actually, I don't know Petro or Christoph is in the audience or not, but no, I think. Anyway, because he is the expert on that topic. So yes, we have a discussion yesterday about it. And actually, what I found a little bit strange, basically, this rogue active region I identified later on during the solar cycle, not before when they are when they are appearing or when they are on the stand.
In principle, they can be identified because they don't follow the Hell's polarity law. So you mentioned that you are also measuring the tilt. So if you make a combination of the tilt and the polarity information, you will be able to identify them.
Ah, okay. Thanks for the suggestion.
So it would be interesting to look at them.
Sure, definitely. Thank you.
Yeah, please.
So I have a comment from the dynamo perspective about the midterm prediction. So while there are some theories about activeness of longitude, these theories have no predictive power. So I don't believe that we are in any state of understanding to be able to predict when and where an active region is going to emerge over the course of the next month or so. In fact, the dynamo predictions that we make are sort of large-scale spatiotemporal averages. So I would say that while you can believe the predictions when you average annually, we don't have predictive power for a month or a 2-month time scale. I cannot tell you how many active regions are going to be emerging over the next month. I can roughly tell you how many active regions are expected over the next year.
Okay. So sorry, maybe I was wrong, not for the couple of months, but for example, for the next week or next couple of weeks. For example, here is this paper that was Rafali, and also I think Motumi also on the co-author. But here they actually starting to develop a method when they studying how the toroidal magnetic field is evolving, and actually when they say the so basically this identifying how this toroidal field is evolving on the south and the north part, and when these two lines are far away together, they say that this is the place where the more magnetically complex active region are.
That's based on observations, right? You observe a nest and then you sort of infer from there that you may have more along the same longitude. Yeah.
Yeah, it's a shallow water. Yeah.
You have to be driven by observations. It's difficult to do it purely by theory, actually.
Okay. Okay.
Thanks.
Sorry, I am still in just beginning and that. But thank you very much. Yeah, definitely. It's nice to learn always.
Yeah, it fits very fast because we are already late.
Yeah, just very fast. So there's something about the terminology, I guess, because you have the short term and the long term. Then you might also have a very short term. You may know that Hugh Hudson and colleagues have been looking at the temperature of the flaring plasmas just before the flare onset. I think he calls them hot onsets or something, just the few minutes before. That can be of interest because they've used it for like trying to time sounding rocket launches and maybe for radiation events or something.
Mm-hmm. Yeah, I know that work. Yeah, that yes. So next time I should add this. Thank you.
Thank you again. Yeah, the last speaker of this session is Cecilia McCormack, a multi-view and multi-point CME catalog based on solo high observations. Hi, everyone. I'm Cecilia McCormack. I'm a postdoctoral fellow for the Solo High team working at NASA. I want to thanks the organizers for letting me present my work here. And thank you to the guys in the back that helped me a lot with the videos today in the morning. In the configuration between Linux and PowerPoint is not the best. So I want to present you the CME catalog based on Solo High, the solar orbital heliospheric imager observations. Just a quick brief introduction. Solar orbiters have different instruments, of course, in situ instrument, remote sensing instrument. The solar orbital heliospheric imager is there in the upper part. We observe white light scattered by electron in the solar wind. We have a field of view of 40 degrees. We are always observing at the east of the sun, as this image here, 40 degrees, and the effective distance in solar radius depends on how close we are of the sun. We have a web page if you want to look at it. We have a lot of information of the instrument and the mission. And the most important thing is we have all the Solo High data there up to date. You can find the data also in the Solar Orbiter Archive and the VSO. And in the web page, you will find an ideal tutorial to
combine the tiles and use the level 2 data. And if you want the Python notebook, please let me know and I can share with you that information. So let's go to the catalog. We have a solo high observation from December 2021, and we start to do like an event list of all the events that we were observing in the field of view of Solo High, but we didn't want to stop there. We want to do like a more comprehensive catalog with a global description of the events that we are looking at. So we start to think in a multi-view and multi-point catalog, and we start to complement all the information that we have in the field of view of Solo High with other remote sensing observation of other spacecraft. For example, stereo, SOHO, PSP. Then we started to track the CMEs to the solar source using SDO and stereo, of course. Then we are going to complement all the events also with a real-time catalog developed by the Moon to Mars teams in NASA, and it's available on Donkey at CCMC. Then we are going to try to understand if any of these CMEs that we observe in the Solo High field of view is impacting in other spacecraft, and we have in situ measurements, and we want to provide that information too. And at the end, we are going to link our catalog with other catalogs so you can have the entire information of the events that we have. But everything starts with Solo High observations. So what we have, this is what Solo High observation looks like. This is an April 2, 2022 event that is super famous. So we have 4 tails. The sun is right here, and we can see well, it's already past. I don't know how to. Okay, you will see this is a super nice CME. We classify the CMEs as good, faint, or super faint. This is a good example because this is a good event that we can see all the structure up to the end of the field of view, but then we have faint event that you lost in the middle, or ultra faint event that maybe are in other direction that we cannot identify that much the structures that we have. So that classification is in the catalog. Then we are going to say when we see the structure appear, the first appearance of the structure in the Solo High field of view, the date and the hours. And we are going to use other classification that is based on the stereo A and B catalog presented by Borlidas and Balmaceda in 2017. They use a lot of labels to classify the structures that they see, but we are going to use only 3 or 4. The first one is the flat row, if we can identify the structures of the CMEs, like the front, the cavity, and everything that we know. The second one is the loops. Here, if we are seeing maybe the CME in another perspective and we only identify the front of the CME, so we are going to use an L, like a loop. Then other, if we cannot identify anything that we are seeing there, like, I don't know if you can see, but here is like a little poof that you can see in the movies. And we are going to label like an O, and maybe if we complement the observation with other remote sensing observation, we will identify better what we are seeing. And also we are going to use a P as a preceding if we are looking at CME that in the back have another CME that is making more complex the interpretation of the one that we are looking at. So all this information also is in the catalog. Then we are going to link the solar map web page with the information of the location of the spacecraft at the moment of the detection in the Solo High. So you will see the position of solar orbiter, Earth, stereo, Bepi Colombo, and PSP. And you will have the table and everything that is already in the web page of Solar Mac. And then we are going to start to complement the information with other spacecraft. In particular, for the remote sensing observation, we are going to link our catalog with the CIDA-Web movies for stereo Core 1 and Core 2, SOHO LASCO C2 and C3 for the same event. And then we are going
When we have the match with Whisper, we are going to detail the encounter and the date that we see the same CME in the Whisper movie, and we are going to link the Whisper web page. Then we are going to find the solar source whenever it's possible. We are going to link the solar monitor web page to provide the HMI magnetograms, and we are going to provide the videos of the movies for the stereo IAU GA 304 and 195. 96, yes, 95, and SGO AIA 304 and 193. And we are going to provide the active region number, the position of the active region number, if it's associated with a filament or a flare, and the magnitude of the flare. If we see the source and UI, we are going to provide that information, but we are not going to provide the movies still. The other important part is that we are going to compare our CMEs with a real-time catalog that the teams of M2M team at NASA is doing. Is the Moon to Mars team. They collect daily all the activity that is happening in the sun. They model a little bit like the half angle and the direction of the CME, and they perform this WSA and LEED plus CON model to predict some impact that this CME can have in another spacecraft. So we are going to look for the in situ data for these predictions and to anything that can be in the direction of the CME. We are going to provide this information that NLEED model is giving to us, but also we are going to provide the plots of the in situ data that we can find for other spacecraft. In this case, Solar Orbiter detected event and it is clear the arrival. So we will provide this, and we are going to look at PSP, Stereo A, WIN, and of course, Solar Orbiter. And last but not least, we are going to complement the information with the information that they have in another catalog. For example, here we have Core 1 catalog that have a lot of information of EUV image, the in situ data also, SCPs. We're also going to link with the LASCO catalog with all the information that they can give you about the observation in LASCO. We are going to use a FLAIR catalog HEC with all the information for those ones that we could identify the flares, and the stereo high one catalog that also provide the image and the shape maps of the event. So for the first release of the catalog, that is going to be soon, we have 140 events from January 22 till April 23. Most of them were detected also in LASCO and Core. Only 6 were detected in Whisper. We have half of the source identified, because mostly in the first semester of 2022, because Solar Orbiter was near the Earth or looking at the part of the Earth. And 26 events were detected by at least one in situ instrument. For the second release, we will have April 23 till March 24, and we had 230 events, but this is a work in progress, so the first release is going to be the 141st. So thank you so much.
You were really fast, so now you will have a lot of questions.
For the lunch, you know.
Yes,
I'll be good.
please.
Thank you very much. Very interesting talk. Maybe I missed it, but are you linking to lists of type 3s and type 2s?
Not still, but it's a good suggestion.
Okay.
Yes.
Okay, because I think it's a very useful catalog. I'd love to use it, or I'd look forward to using it, but it would be very useful to understand SEPs and CMEs, but you know, the key is the type 2.
Type 2, yes,
Yeah.
totally. Well, we thank you for the suggestion. I want to complement all the information for the community to have a global view. So we are adding SCP already, but I will start with that too.
Okay, and then just I'm the PI for Solar Monitor, but we have a new Solar Monitor, so the URLs are all going to change very soon. So
Okay.
maybe we'll talk afterwards.
Yes,
and
let's
show you.
talk.
'Cause it's a Python-based system now. And
Okay.
it should be easier for you to link to given active regions.
Okay, perfect. Thank you
We'll
so
talk
much.
later. Okay, thank
Yeah.
you.
Yeah, maybe I missed it. In Hellcat, if I recall, they're using something modified cactus to identify the CMEs. So what is the algorithm you are using in your catalog? The
No, we are
identification?
doing everything manually. Like
So
yeah.
no automated.
No automatic. I'm going day by day.
Okay.
That's why I'm
Okay.
2022 is you.
Tough
Yeah.
job, tough job.
Okay, so, oh. No, because for the people that are in the Zoom, yeah.
Speaker, I just want to ask, do you plan on automating the catalog collections in the future?
Well, we are trying to automate this the detection in the Solo High, but as you saw, I don't know if you saw the movies of Solo High, because I don't know, maybe you have more information than me, but when you want to do something automatic, you need to have a clear image like this. But the thing is that for Solo High, we have a lot of change of pointing in the solar orbiter. So we have jumps in the movie, like we have black out in some of the tiles of everything that make the automatization a little bit hard. We are working on that, but slowly.
Okay, so let's thank again Cecilia. Thank you. And Marco, there are some announcements, no? So we reconvene at 1:30. Okay.
No. The slides. Okay. Okay. Oh, okay. The slides. Okay. Okay, good afternoon, everyone. My name is Abigail Mtetwa. I'm a master's student from the University of Johannesburg. So my master's project is on determining if ghost ultraviolet measurements can help predict the X-ray properties of solar flares under the supervision of Prof. Snow and Prof. Winkler. So I'm gonna skip this because of time. So a solar flare is a short and intense blast of high energy radiation from the sun that occurs when the sun's magnetic field lines get entangled and snap. So here is a short movie of a X-class flare that occurred mid-February this year. So basically what happens on this panel, as you can see, is that magnetic energy builds up in the solar corona due to the motion of the sun's plasma. This distorts and stresses the magnetic field lines. And then something disturbs this configuration, leading to magnetic reconnection. Here, high energy particles, electrons and ions are accelerated down the field lines, and then they hit a denser, lower solar atmosphere, the chromosphere, and we see the flare peaking in the magnesium 2 index. And then we get chromospheric evaporation, and in the last slide, we get chromospheric evaporation and plasma is heated in the transition region and the corona. And we see the flare peaking in the extreme ultraviolet and the soft X-rays. So the aim of my project is to better understand The aim and objective of my project is to better understand the characteristics of solar flares by analyzing the ultraviolet solar spectral irradiance measurements. Sorry. By analyzing the solar spectral irradiance measurements from GOES extreme ultraviolet sensor, and the goal is to use high cadence operational measurements from X's to make real-time predictions on X-ray flare class and duration based on clues from helium-2, Lyman alpha, and magnesium-2 observations. And with this real-time predictions, establish a flare model that will be used by space weather forecasters in real time. So this is just a summary of what I just said. So the methodology that I followed is that there's already available data on the NOAA web page for GOES, and on board GOES is the Axis instrument that contains the extreme ultraviolet sensor and the X-ray sensor. The Axis is always facing the sun, so this gives a more detailed and reliable information on solar flares. So I'll be analyzing only the big flares, the M and X class. And so far we have about 45 X class flares and about 822 M class flares. And then And then on this diagram, you see all the spectral lines that I'll be analyzing, the X-rays in the corona, the helium-2 and Lyman alpha in the transition region, and the magnesium-2
index and the chromosphere. So what I've done so far, especially in this presentation, I'll only be focusing on Lyman alpha, not the other two spectral lines. And as we know that X-rays vary over about 2 orders of magnitude in the X-ray. Solar flares vary about 2 orders of magnitude in the X-ray portion of the spectrum relative to the background, whereas the corresponding increase in Lyman alpha can be considered marginal due to the high background at this wavelength. So I used a file which is already available on the NOAA webpage, which contains the background flags of the X-rays. That is what I use to subtract the background from the X-rays. And then from the extreme ultraviolet, Lyman alpha in this case, I consider the background to be an average of a few minutes, about 15 minutes before the flare occurs. And then these are just histograms of the X and M class flares that show the percentage increase of Lyman alpha above background. And as you can see for the X class flares, it's about 7%. The extreme case is about 7%. And then for the M and X class flares, it lies between 3 and 5%. Milligan had started a similar case in 2022 using 477 M and X class flares and found that about 90% of them have a 10% Lyman alpha enhancement above background with a max of about 30%, which is relatively what I have here, except I don't have the extreme case in my data set. And then this is a histogram that shows the flare duration. And as you can see in this this is the flare duration histogram. As you can see, the M and X class flares are evenly distributed across the entire histogram, meaning that the X-ray strength, the flare strength is independent of the duration of the flare, vice versa. And we can see that most of the flares start and end at about 20 minutes, 25 minutes max. And then, but we've got some extreme cases where the flare would last for about an hour or more. Nathan identified this as long duration events, where the flare lasts for more than an hour above background. And then here we've got a histogram that shows the distribution of the flares on the solar disk, with 0 arc seconds being the center of the disk and going towards the limb of the disk. And from this presentation, as you can see, there are more flares on the solar limbs than they are at the disk center. And then I also looked at the duration of Lyman alpha versus the duration of the X-rays to see if the duration, if Lyman alpha peaks first, if the duration can actually help in predicting the duration of the flare in the X-rays. As you can see on the blue dots, the blue scatter plot, which are the X flares, they are well correlated, the duration of the X-rays and the duration of the Lyman alpha. This would be very useful if Lyman alpha peaked maybe an hour or more before the X-rays, because then we'll be able to actually determine how long the X-rays will last. But then since the peak in Lyman alpha and the X-rays the difference is about 3 minutes. So when Lyman alpha is decaying, the X-rays are also decaying. So we can't tell much from that. And this is just the M-class flares, which showed 2 different correlations. And then I considered the flares that are above, where Lyman alpha has a duration of above 40 minutes. And this is the graph here, which shows relatively something similar to the X-class flares. And we can't really conclude much from that. And then I went ahead to categorize the flares into 3 categories. Type 1 being where Lyman alpha peaks before the X-rays. Type 2 being when they peak at relatively the same time. And type 3 when the X-rays peak before Lyman alpha. And as you can see, majority of the flares, we have Lyman alpha peaking before X-rays, which is a good thing because I'm trying to use the properties of Lyman alpha to determine the properties of the X-rays. And in those 3 types, I further looked at the flare duration versus the strength of the flare. And as you can see, there's still no correlation between the 3 types of the flares to the strength of the flare. And then I plotted the 3 types on the solar disk, the side. And as you can see, all the 3 types are distributed across the entire solar disk. So it does not matter what type it is, it can fall on either side of the disk, of the solar disk. And then this is just some statistics on the flares you are looking at there. So you can see region 1. Here on the solar disk, I divided the disk into 4 regions, region 1 to 4. And as you can see, region 1 and region 4 have way more flares than region 2 and 3. So when I calculated the area of the solar limb and the disk center, I found out that at the solar limb, because it's a sphere, it's not necessarily a circle, there is more area on the solar limbs. There's twice more area on the solar limbs than there is on the disk center, which makes sense because that means an active region spends twice as much time on the limb than it does on the disk center. Hence, we have more flares there. And then this diagram here shows that most of the flares that I'm analyzing, about 70% of them are type 1 flares, where Lyman alpha peaks first, so which is a good thing, and which corresponds to the model that I was talking about earlier on, that the flare peaks in the magnesium 2 and Lyman alpha before the X-rays. And then the type 1 flares that I was looking at, I considered the strength of Lyman alpha versus the strength of the X-rays. And in this case, I added the B and C class just to see if this trend is very similar to all of them. And as you can see in this diagram, not 100% conclusive, but as you can see that in this diagram, if Lyman alpha peaks to less than 10 to the -5, then it is highly likely that the peak in the X-rays will be an X-class flare. And if it peaks less than 10 to the -6, it's highly unlikely that it will be an M-class flare, and so on. And then recently I am looking at, since I was looking at the magnesium 2 index, now I'm looking at the ratio of the H and K lines of magnesium 2 just in the chromosphere. And I saw that Roy, another paper that I was looking at, they were also looking at the variation of the ratio of the H and K lines for 3 flares, the X and M class and C class flares, but using iris data. So I'll be using ghost data, and their results show significant changes during the evolution of the C and M class flares. This is just a coincidence that the ratio also shows a great significance for a C and an M class flare, but I haven't looked at the X class flare, so I cannot conclude now. And this is a scatter plot that shows the change in the H and K line ratio to the change in the flare flux. So this is not conclusive yet, and I've only looked at quite a few data sets. So I'm still going to look at the whole year and see if there's a pattern there. So this is not limited to the things I have analyzed, and the no's show no correlation between Lyman alpha and X-rays, and the maybes are still being scrutinized. Thank you.
So thank you very much, Abigail, for this very nice presentation. We still have about 2 minutes for questions. Are there any questions for Abigail? There's a beautiful piece of work for your master's thesis that you did there. Okay, yes, let's thank her again. So our next speaker will be remote. That's Radoslav Buček. Radoslav, are you there? Can you hear us?
Yes, good afternoon, everyone.
Properties of solar surface. Oh, sorry. Magnetic field properties of solar sources of impulsive solar energetic particle events. Ah, there he is. Hello, Radoslav.
Yeah, hello. It is any change in the plan? Should I present right now? Not at
yes,
2:15? I'm fine.
This is the program as of today that the organizer sent to me.
Okay.
Would be perfect.
No problem. Okay, I will share my screen.
Okay, then.
Yes. So
I will come and tell you when you have 2 minutes left, okay?
Okay. So my name is Radoslav Buček, and I'm a scientist at Southwest Research Institute in San Antonio, Texas, and these are my collaborators. In this presentation, we examine magnetic field properties of solar sources of impulsive solar energetic particle events. So here we have a cartoon which just show briefly what are impulsive or flare or jet-related SCP events, and here we have what are gradual or CME shock-related events. Impulsive SCP events show unusual abundance with helium-3 and ultra-heavy ions, enhanced by a factor of up to 10,000 above the coronal values. So this figure shows enhancement factor of impulsive events above the corona versus mass in atomic mass unit. Some species like helium-4, carbon, nitrogen, oxygen are not enhanced in impulsive events, but other heavier ions show increase in enhancement factor with mass. For example, iron is enhanced by a factor of 10. This results from unknown mechanisms during magnetic reconnection in jets. So we may ask, how do magnetic properties in solar sources affect the heavy ion enrichment and intensity? We selected the extreme events where we think the effect of the magnetic environment in solar source on particles could be most noticeable. We search for high energy, impulsive SCP events, which should be less affected by transport in interplanetary space and magnetic connection. They also have a higher impact on space weather. Second criterion, we search for highly helium-3 enriched events with helium-3 abundance greater than 1,000, the coronal value, to exclude helium-3 enriched gradual SCP-CME shock events. Such gradual SCP shock driven events are really measured, and helium-3 enrichments can be of factor 100 or even more. So results. Using these conservative criteria, we identified 21 events in January 2008 to July 2021 detected by solar isotope spectrometer above rays. GAUSS C-class X-ray flares were in 83% of events. Few events were B-class and M-class. Type 3 radial bursts were in all events, and type 2 bursts in any. CMEs were reported in 71 of events where 80% have speed less than 500 kilometers per second. So these events were likely not helium-3 rich gradual SCP events. SDO and stereo observed jets in 81% of events and brightening in the remaining events. So this is example of intense high energy helium-3 rich SCP events with extremely large helium-3 to helium-4 ratio and helical jet in the source. This event occurred on February 18, 2011. So here we have intensity versus time, and with the red dots is shown helium-3 at energy 10.5 MeV per nucleon, and with blue dots, it's shown helium-3 with energy 5.2 MeV per nucleon. Helium-4 is shown with black curve. This event is associated with single strong type 3 radio bursts. As far as source region for these events, NOAA Sunspot Group reports active region with the most complex beta gamma delta magnetic configuration and maximum area 670 millions of the solar hemisphere. So this is the on the right side we have a full sun in it is difference image in 193 angstrom from SDO IA. This bright region is the source of these impulsive events, and black cross is a magnetic foot point. Bottom panel is a composite image consisting of a magnetogram and 171 angstrom wavelength from IA. So you could see very complex active region and helical jet at the boundary. So this should be a movie showing twisting jet at the boundary of this large and complex active region. The area and magnetic class of an active region are reported usually once a day at the NOAA Solar Region Summary. But we want characteristics of active regions close to the flare or type 3 burst time. So we use sharp parameters. Sharp are derived from the HMI SDO vector and line of sight magnetic field, and have a 12-minute cadence. So this table shows sharp parameters we use in this work. This is keyword, description, and formula. Two are derived from the line of sight magnetic field, like area of strong field pixels and R value. These few slides, I will show a few description of sharp parameters. For example, these sharp parameters, mean GAM, indicates magnetic morphology. These three sharp parameters could be grouped together and quantify the complexity of the active region. These sharp parameters describe the pitch angle of the field twist. Also, these three sharp parameters could be grouped together, and all are measure of the extent to which an active region stores energy above the supplied by the lavast energy configuration. Other three sharp parameters could be grouped together, they are measure of the topological properties, so and so on. And we also use these last four sharp parameters. So as an example, I selected one sharp parameters, in this case, area of the strong pixels in the active region, and examine temporal evolution for each impulsive event. This vertical red line shows time of the type 3 radio burst, and we show evolution 4 days before type 3 radio burst and 1 day after. This number here is the longitude of the active region. For some events, we don't have sharp parameters like here because source is behind the limb. Also here. So we exclude 6 events with solar longitude where the source have solar longitude greater than 80, where sharp parameters are not available or affected by projection. Notice that studies on solar flares rejected active regions outside of the area within ±78 of the central meridian. So we are not so far. This is similar for another sharp parameters, which is characteristic twist parameter alpha. I mentioned earlier that we identified 21 impulsive events. However, one event doesn't have sharp parameter, so we show only 20 impulsive events. We calculate 3-hour mean value for each sharp parameters prior type 3 radio burst. And do correlation. We correlate, in this case, helium-3 flux at energy 10.5 MeV per nucleon with each 3-hour mean value of which 3-hour menu of each sharp parameter. So we have here 18 different sharp parameters. These dots shows values for impulsive events. And what we found, fractional area with share greater than 45 degrees show the highest correlation. Here. The horizontal gradient of the total field show no correlation. So we do the same for the helium-3 to helium-4 ratio.
Radoslav, 2 more minutes.
Yes. Yeah. And we find that the horizontal, the absolute value of the net coherentity show the highest correlation, and these two horizontal gradient of the field and the vertical coherentity show no correlation. So summary, as far as helium-3 intensity, 2 sharp parameters show no correlation, 5 show weak correlation, and 11 show moderate correlation. Concerning helium-3 to helium-4 ratio, 5 sharp parameters show no correlation, 8 parameters show weak correlation, and only 5 show moderate correlation. So these results indicate that helium-3 intensity is more closely related to the sharp parameters than helium-3 to helium-4 ratio. It can be the effect of helium-4, which is not preferentially accelerated and might destroy the correlation in helium-3 to helium-4. And finally, the helium-3 to helium-4 ratio shows the strongest correlation with the absolute value of the net current helicity, which is a measure of the twist in the vertical field. And you remember this, I showed this event with the extremely high helium-3 to helium-4 ratio and the twisting jet. So it looks like the ratio is related to the twist. And helium-3 intensity shows the strongest correlation with the fractional area with share greater than 45 degrees, which is a measure of the extent of the extramagnetic share. So it looks like that intensity is related to the area of the extent. So finally, these correlations which I presented need to be inspected for outliers also in these preliminary results, and more events must be included, for example, by relaxing of the criteria or including the events from the recent solar cycle. Thank you.
Thank you very much. So we have 2 minutes for questions. Are there any questions here in the room? I cannot see any hands raised, so it looks like this talk was as clear as the previous one. So thank you very much again, Radoslav. And we move over to the next speaker. That's the last talk of this session. And that's by Angelos Volidas. It's an invited talk on improving the medium-term forecasting of space weather, a big picture review. And here is Angelos. You can hear us, Angelos?
Yes.
And we can
I can hear you. Thank you.
5 minutes, and I will give you a 5-minute warning if that's okay.
Thank you. Hi, everybody, and apologies for not being able to make it on time to the meeting. I really want to be there in person for this one. So we'll do the best we can. So I was going to discuss kind of a big picture review of where we stand in terms of forecasting what I call medium-term space weather, and that's sort of as a prelude to the discussions that come in later in this session, but also as an overview of where we stand at the 2024 in terms of solar drivers of that weather. So this work is really driven by my experience with working on the programs like Stereo Parker Probe Solar Orbiter all these years. So first, let's establish the what we're talking about. So space weather is really just the effects of the solar drivers on the Sun-Earth system. And therefore, there is a very complicated process between what leaves the sun, which we call the solar drivers, how that hits that interface of the magnetosphere, ionosphere, and thermosphere, and then that creates the sort of the actual effects of space weather that are quite complex. So there's a lot of history, let's put it that way, between what leaves the sun and what actually we experience here on Earth. Now, these steps, if you like, in the process of predicting space weather can be cut into different prediction regions. And what I call medium term in this case is just hours per days, what we actually see on the sun with our telescopes and we experience as flares or CMEs or shocks, and trying to make a prediction out of that. Then we have, of course, the more immediate predictions when these drivers cross the L1 or other satellites that we have in the near Earth space, where based on those measurements, we can make some sort of a almost nowcasting prediction. And as you can see, these different regimes, I try to allocate them in sort of different areas of responsibility. Now, in our case, what we care about is the medium term, which is primarily, and it was up to very recently, a NASA sort of a research agency type responsibility and basic research. So the effects that we're talking about is really coming in mainly through CMEs. And again, this is a summary, a very top level summary of the effects I'm talking about. So CME is really driving most of the space weather because they have most of the energy to impart into the sun, into the ionospheric system. As you can see here, I try to allocate how we actually do this forecasting. And for most cases, of course, we rely on imaging because we're looking at things very remotely at the sun, and then use some sort of a modeling infrastructure to come up with the forecasting. So the imaging, and I'll be talking, of course, mainly about imaging, is the key, if you like, capability that we need to improve on if we want to improve on the forecasting. So where do we stand? Where do we stood, I guess, 20 years ago? Since that's where I'm starting my review from, 2004. Well, we had SOHO, and SOHO was really what the Space Telescope has been for astronomy. We sort of reinvigorated our discipline. In terms of the space weather, the big impact was the combination of coronagraph data, and here I have a combination of the LASCO C1 in green and LASCO C2, and then a 304 image from EIT in red. This combination was, of course, the first time we actually had it in a persistent way, and we were able, therefore, to track the transients or the CMEs from their origin on the disk to the inner corona. So that led to several sort of key filling key knowledge gaps, which I summarize here as the realizing that CMEs are essentially magnetic flux ropes, that they do have low corona manifestations beyond the flares, and that's what really the EUV was an eye-opener, the EUV capability. And thanks to LASCO, basically was firmly established that indeed it's not the flare that sort of is the cause of the the space weather, but sort of the ejection and the eruptive phenomenon as a whole that drives this. That was a big debate actually in the 90s, so 80s and 90s. Now, the other things, of course, we got a lot of other information about CMEs. We were for the first time able to get rates, measure kinematics, and of course, associate with all this other sort of collateral damage, if you like, that the ejection causes in the corona, including radio emission and energetic particles. Now, to me, if I was to say what was the key result from these imaging observations in terms of space weather, would be the realization that CMEs are flux robes, because that drove a whole industry, if you like, of modeling and, of course, propagation, time of arrival or propagation models that we still, very active today. So this is sort of the initial, if you like, steps towards realizing that there is a magnetic structure coming out of the sun, and that's the important thing to space weather. Now, after that, of course, we got the stereo mission that was the most unusual mission, really, in astrophysics, trying to image the star in 3D. But not only that, we were able to image for the first time the solar wind in interplanetary space. And here's an example, of course, that I also often use from 2010, where we can see so many CMEs coming towards Earth, and the Earth is actually in the field of view. So that's mentally, again, is the sort of imaging that clinches the fact that the sun and the Earth are really interconnected. Now, thanks to the multi-viewpoint imaging, we were able to now track CMEs into the heliosphere. So again, for the first time, we have this ability to kind of tell where an event is heading towards, maybe not with great accuracy yet, but we do have the capability that we didn't have 20 years ago. So again, if I was to summarize the stereo results, I would say the main thing was that we managed to get at least the 3D structure of the large-scale structure of those phenomena, recover it to quite a good degree. Did establish that there is a magnetic flux rope hiding in that structure, and also for the first time we imaged both the CMEs, or the planetary CMEs, as it used to be called in the old days, and co-rotation interaction regions. Other the things that came up through stereo and are still an active part of our research is the comparison for the first time between in situ and remote sensing. I'll come back to that. Realization, of course, of effects. We can actually see the interactions and the effect they have on the structure as they propagate in interplanetary space, which is of a big value to improving forecasting. And the wide range of ACPs, that it was sort of gleaned from in the past, but this time we had very sustained observations with the two stereo telescopes and the in situ at the Earth L1 point, the in situ instrumentation. And I will come back to the hot flux ropes right now. So if I was to say what we sort of learned for doing midterm forecasting, of course, the first thing is that we need continuous coverage of the solar activity. This is, if you like, a typical day in 2000 in cycle 23, which is similar to our cycle now 25, because that's really what allows us to make the connection between activity at Earth and activity on the sun. And I think that we cannot make any more progress without having this basic capability in any of our future missions. The other thing, of course, the realization was that the flares, in a way, flares were not the only thing associated with eruptivity, but that the actual eruption, the movement of the plasma, of the coronal plasma, as a result of the energy of the release of magnetic energy, actually has imprints on the surface, which can be used and are being used to determine or estimate a lot of the properties of the CME even before it appears into the coronagraphic field of view. And so this is a slide that actually put together 20 years ago for the SHINE meeting. And basically this describes the very early results that have now been thoroughly established. However, there was still an open issue, and these effects did not tell us exactly what many people think about the flare and CME connection, and I'll get to this later on. Now, the other big capability, I think, that a lot of people are using, and people in the audience, is the ability for us to do not only the construction of the CME, but also of the shock. We realized with LASCO that we do see the shocks or the waves, if you like, that the CMEs are creating as they propagate outwards. But now with 2 or even 3 spacecraft at hand, we can do very detailed reconstructions of basically the whole response of the large-scale corona to an emerging flux rope. And that allows us not only to get 3D information like that, but also to get velocity fields. I mean, it's a complicated process, but still we can get some sort of a velocity field and understand the kinematics of the plasma that is participating in this erratic process. All these thanks, of course, to multi-viewpoint imaging. But to me, this was the most unique paradigm shift in the last 20 years, that it doesn't have to do with coronagraphs, and that's the realization that a lot of activity that in the low corona was escaping our attention because we didn't have hot channels or sensitive hot channels in the EUV imager, say in the AT. And so the inclusion of 131 from SDO to me is the most important and useful result coming out of the whole project. And as you can see here, it's an eye-opener because it tells us that a lot of activity is going on in the low corona, but we do not really have the capability to identify it very well. Yes, now we have 131 and we can see maybe those 10 million degree plasmas, but what if there are cases that the plasma is for some reason, isothermal configuration that escapes the current distribution of channels that we have available. Of course, one can think that we may want either white light observations, which is very difficult to achieve so close to the limb, or a lot more channels, or picking the channels very carefully to whatever the objective is. So in statistics, this is not something unusual. This is also a work we did, and we realized that 50% or more of the eruptions have this hot flux unseen before hot flux rope if the viewer has the right line of sight. So again, there might be situations where we miss this particular feature just because it's it's projected in the wrong way along our line of sight. So again, that's where multi-viewpoint imaging needs to be considered. So if I were to say where we stand right now, I have 4 big points. 24/7 observations, of course. The joint EUV and white light observations, which now has become part of the operational payloads. So it clearly is the way forward for, at least for operational forecasting. But the multi-viewpoint imaging, we cannot really rely on single, sun line observations to learn anything more than we already know. And of course, the hot flux ropes, that the realization that there might be features of that eruptive process that escaping our attention just because we do not use the right wavelength or we don't have the capability for that wavelength. And so for future results, these are sort of my justification for using those, coming up to those 4 big results. Now, there were some paradigm shifts, and that's for space weather forecasting. And the main one is this to me, that we don't need a strong cycle or be at the peak of the cycle to have a dangerous event. The biggest event that we had in the last, 50 years, 60 years was this CME in July 2012, which was really on the peak of cycle 24, but that cycle was very low. And that event seems to have been, if it had hit Earth, it would have been even bigger than Carrington. So much for high activity and correlations with sunspots and all that. This is not really the important thing for space weather. Now, the other thing that this event drove is the need of making measurements well ahead of L1. In this event, for example, if we had an L1 monitor, we only have 10 minutes to sort of issue a forecast about the magnetic field strength in particular, which is, of course, impossible. That's going to happen. So we need to be thinking about some other locations if we really want to do more successful forecasting. The other thing that gets me back to the flares and the connection between CMEs and flares is that the realization that the flare and the CME, or if you like, the magnetic ejection, if you like, develop at the same scale. This work we'll be doing for a while now, and I did report on that back in 2010-11, that what we see from the EUV analysis, the 3D analysis we do, is that the CME expands laterally very fast, but for a very short time. And here is some recent results from we worked with Laura, where we saw that the CME aspect ratio, and these are two aspect ratios along the radial and across the longitudinal. When you look at this aspect ratio, there's a very sharp increase to it that occurs within 3-4 minutes, that it correlates with the impulsive rate phase of the flare. And that basically drives a wave, drives a shock. You can drive the particles, and therefore association of particles with impulsive rate of the flares means nothing about that there is a cause and effect, right? For me, these results do again suggest that all the particles are accelerated. It shocks low down in the corona. And there's further results here where you can see the connection, for example, between the speed of the lateral expansion, and when the lateral expansion reaches sort of a peak, that's when the metric type 2 starts, which you would expect, sort of things you expect once you see them in plots. But sometimes this can happen before the X-rays. And again, the timing between metric type 2's X-ray peaks and energetic particle injection scales, it's not so simple. You cannot just use that to say, oh, this is related to the flare. I think it's all related to the magnetic energy release, and whether there's a flare or not is sort of an energetic question, not a cause and effect question. This is my big issue, as always, and you guys know me that the projections are everything when it comes to coronagraphs and measuring CMEs. So this is the same CME, measured at the same time between core 2 and P, and they're only 70 degrees apart. They're not even in quadrature. And then, well, what is the measurement? What do you correlate with what in this picture? If you had only the right-hand side, you might make a measurement, say, with a lower question mark here for the CME envelope. Yet there is potentially a shock or a wave going around that an observer might not be tuned to it unless they had an off-the-sun line measurement. And that's why I'm saying that for improving the medium-term forecasting, you actually need off-the-sun line measurements, not coronagraphic measurements from L1 that don't really provide the key parameters that we need. So where are the open issues? At this point, to me, the biggest open issue is the CME propagation. Here's a movie that probably, I don't know if it plays well over there, of some sort of a highly processed high 1 image where we have two CMEs interacting. And as you can see, even though we try to do as a clean processing as possible, still we have to rely on some sort of a running differencing scheme where it sort of creates more structure than it might be there, and sort of confuses the structures that we see going out. So it makes it hard to track the magnetic flux rope relative to, say, the shock, or to attribute a particular structure to something in the lower corona. And so that really, the farther away the CME goes, of course, the more diffuse the structure gets, the more pileup occurs around the event that may overshadow or confuse the internal structure. And so that really creates issues when you're comparing with in situ. And what this, if I learn anything from the SECI measurements, is that the in situ measurements are very uncertain.
Angelos, 5
Yes, yes, very uncertain. And so we have a big gap in our understanding between what we measure in situ and what that represents in terms of the large scale structure. One other issue that we found with CME propagation is that multi-viewpoints are not necessarily improving the predictions that much. And that's again because, and I think it's because we are not really capturing the small scale structure or that actually arrives at Earth very well from 1 AU. So the 2 viewpoints give us the large scale structure, but the precise forecasting depends on the smaller scales, the mesoscales, if you like, which in order to recover them, we need higher dynamic range imaging out in the heliosphere. But the biggest issue, and that's really the bottleneck that I don't see how we can improve on, is that yes, we know there is a small flux rope coming out in the CME. It's embedded somewhere in the big event. It looks small, of course, in terms of the sun, but as you can see, the modeling suggests that this flux rope evolves. There's a connection with its surrounding structures, with the ambient, possibly internally. And when it comes to Earth, the CME, as you can see, it's the core of the CME is maybe 20 to 30 solar radii wide, and the Earth is nothing much but a very small sub% of that structure. So if you want to get accurate prediction, you do have to understand the incoming structure to that level, which I don't think is possible at this point. And so that will always be our sort of bottleneck for the future. So top knowledge gaps, I will put them again, is really what's happening in the interplanetary space. And that's something that we still, I think we have good enough data to evaluate better. We don't really see the inner corona very well. We don't capture this 1.5 to 3 solar radii very well, except for eclipses in terms of resolution. And so that's another area that we should be focusing on. And of course, the physics, energy balance and force balance and energy budgets are not very well understood in the events, particularly as the event evolves into the heliosphere. So this is my final slide. I still think that we should keep those 3 bullets in mind for anything that we're thinking of the future for space weather forecasting. The cycle does not matter. Okay, what matters is what is the configuration of the active region on the surface, and I'm sure Sami will agree with that. If we have a delta inverse Hale law configuration with a lot of flux emergence, well, you don't need magic to predict that there's going to be a big CME or multiple CMEs out of it. The question is when. And if we were to go for more specific physics challenges, these are my 5 challenges that we need to improve. And I have, of course, implementation parts in the last column. But the CME field and the magnetic energy buildup at the source, I think, are the key attributes that we need to improve upon if we want to improve forecasting. It will give us sort of the most bang for the buck. Thank you for your attention.
Thank you very much for this nice overview. Are there questions? Yes.
Hey, Angelos, Peter Gallagher here. Nice talk. Tell me about LASCO and where it's going and what's going to replace it. It's been a workhorse for, predicting CME arrival times at Earth for the past decades.
Yes.
Tomorrow, what do we do?
Yeah. So the plan, okay, C-Core has been was launched on GOES in mid-June, and so it should finish commissioning. It starts commissioning in September and should finish by January, so that then we have an operational, presumably chronograph, replacing LASCO. LASCO will stay on until the L1 chronograph gets in place, so until end of 25, beginning of 26, if IMAP launches in mid 25. At that point, my plan is to petition NASA, and I'm going to talk to Jack, and I have already talked to the folks at Goddard at ESA to keep going as a science mission, basically to become an infrastructure mission and go until the end of the cycle, so that we can collect 3 cycles, exactly 3 cycles with the same instrumentation for future, historic analysis, and that would be the plan. And I'm quite optimistic that it will happen, unless this, of course, we'll lose the LASCO.
Happy to support that in any way I can.
Okay, Dipankar.
Hi, Angelos, this is Dipankar here. So again, CME propagation part in inner corona, what we are now calling middle corona, 1.3 to 3. Another property I think we have been reporting now recently is the dispersion within the CME. And making the life even more complicated. It's not a very simple 3-part structure which is moving into the interplanetary medium. So how do we tackle this? Because the self-similar expansion, all these standard models doesn't seem to be very well working.
Yeah, so the self-similar expansion, I'm not saying that, I cannot agree with you. It seems to be working because the angular width of the CME is, as projected, is quite constant.
Yeah,
sure.
Beyond thing 5, it is okay. Right. But this distance which you are referring to, we see really large dispersion. So how do we tackle that?
Yes, so that's why I mentioned about the lateral expansion. And for example, this is the picture. Maybe you are referred to the last view in how it looks in the EUV and how you can maybe be able to track it in a coronagraph field of view. So to track this, yeah, you need high resolution, high cadence imaging so that you can do a better optical flow analysis. So I have that. I made some tries with LASCO, with Seiki Core 2, and we took 2.5-minute cadence observations, and there you can track a lot of that evolution. But again, this is all projection. So the question is, what are you trying to track? The CME overall may not be important for the space weather. It's that magnetic flux rope in the center of it that you want to track, and I don't think that experiences any weird forces or non-self-similar expansion. But high resolution, high cadence imaging, yeah, that 2 to 5, 6. 2 to 5, yeah.
Thanks.
Okay, there's time for one more short question.
So in your wish list, you had a line of sight magnetograph at L5, but wouldn't require a magnetograph for measuring twist, which could be useful for figuring out the and also then its impact on the TST?
Yes, that's right. So I don't know if though that you need that at L5. The vector, the twist, you need it. You can take it from the L1 perspective because that's the structure that will come towards you. But that has to happen in the upper chromosphere, right? The photospheric stuff is just the clutch that we have. The phenomenon do not happen in the photosphere. They happen in the low corona, upper chromosphere. If we can get that vector magnetography at this 1 arcsecond type scales, then I think and measure the twist or the rate of twist, then I think we got it. We will know when the CME will erupt.
At the cost of going over time, I can add to that, Angelos, that there will be a vector magnetograph on ESA's Vigil mission at L5.
Mhm.
And it's not just about the twist, it's also about solving the 180-degree ambiguity and a lot of other stuff. But okay, I'm going to cut myself short because I can talk forever on this topic. So let's thank Angelos and all the speakers of this session. And we now start a brand new session on the sun-space weather connection. We are starting with an invited talk in person by Vincent Ledvina. And the topic is, oh my God, that's a long title. How open data and interdisciplinary collaboration improve our understanding of space weather, a risk and resiliency perspective. Okay, you have 25 minutes.
All right. Hello, everyone. My name is Vincent Ledvina. I'm going to be talking today about space weather, specifically how open data and interdisciplinary collaboration improve our understanding of space weather, a risk and resiliency perspective. Before I begin, I just want to thank the conveners for giving me this opportunity today, as well as my co-authors for all their help on this work. So here's a really brief outline of what I'll be covering. First off, my perspective, so where I'm coming at with my perspective, my background with space weather. Then I'll briefly go into space weather and its effects. So we've already been hearing a lot about space weather, but just it's always good to have a little bit of an overview. Then I'll be motivating why we're doing this risk and resiliency framework. It's basically a new context for how to approach space weather and society's readiness to space weather impacts, and some potential solutions within that framework are open science and data science, cross-disciplinary science, information systems, international collaboration, and citizen science. So I'm a space physics graduate student at the University of Alaska Fairbanks, entering my second year of a PhD program. I actually got into the field through aurora chasing. So I was in high school and growing up in Minnesota. If you don't know where that is, your US geography, it's basically on the border between the United States and Canada. So in order to catch these auroral displays at those latitudes, you need to kind of know a little bit about space weather, track the data, things like that. So I was looking at real-time solar wind plots when I was 16 years old, a little bit of a nerd, but that's really how I got into things. And then this work, so, you know, I went to undergrad in North Dakota, and then this work came about through a conference called the Eddy Symposium, which is a meeting of space scientists, climate scientists, sun scientists, and planetary scientists. And we had a working group called the Risk and Resiliency Working Group, where we looked at, you know, are we ready for a space weather event in 2022? It was in 2022. So we all came together. We had some really good discussions, and then I led an effort to publish a white paper in the Heliophysics Decadal Survey, the last one that went out, and then further on a peer-reviewed paper, which I'll have a QR code at the end of this presentation where you can look at all the details. But that's really where this is all coming from. And so now, what is space weather? Well, we should all know this, but as a little bit of a reminder, it's referring to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. Space weather disturbances really come in 5 flavors. You have coronal mass ejections, or CMEs, solar flares, solar energetic particle events, or SEPs, high-speed streams, and stream interaction regions. These 5 space weather disturbances can affect 4 main industry domains, so ground infrastructure, high-frequency communications, near-Earth assets and services, as well as aviation. And the space weather disturbances really create 5 major space weather impacts. So these impacts can occur at all the same time from multiple disturbances happening, and can affect all 4 industry domains at once. And since we're in solar maximum, of course, this is happening more and more often. There are radio blackouts, geomagnetically induced currents, or GICs, effects on satellite infrastructure, effects on humans working in the atmosphere and space, and also single event upsets. So just really briefly, I'm going to go through each of these impacts. So radio blackouts occur from solar flares and radiation storms, where ionization occurs in the upper atmosphere that makes an opaque layer to high-frequency radio signals. So HF comms are relied upon by aviation and shipping industries, emergency responders, amateur radio operators, and the military. When these radio bursts are high enough frequencies, they can also affect industries like mobile phones, GNSS services, and satellite internet. And critical infrastructure is resilient, right? These radio blackouts happen on a daily basis during solar max, but even sort of minor space weather events have caused incidents. So just as an example, there was a radio burst on December 15th, 2023, from a garden variety X-flare, X1.5, X1.7. These happen all the time during solar max. But the actual radio burst itself was long-lived and affected a very high frequency range. So if this had gone on any further, they were actually thinking about shutting down airspace over the entire Pacific Northwest in the United States. Geomagnetically induced currents may occur during times where you have strong magnetic fluctuations in the atmosphere. So if you remember your Maxwell's equations, Faraday's law tells you that if you have a dB/dt time change in magnetic field, that transfers down to a current in the ground. So this could occur during geomagnetic storms, substorms, as well as sudden impulse events. And GICs damage infrastructure, particularly transformers and power lines. And primary risk areas are around the poles and underneath the auroral ovals, although there have been instances of GICs observed at lower latitudes. Satellite infrastructure is affected by space weather in two main ways. During geomagnetic storms, joule heating and other effects increases the neutral density at higher altitudes. Essentially, the thermosphere expands. So this affects satellites in low Earth orbit. You're not expecting neutral density, and then it occurs, and suddenly you have to worry about adjusting your trajectories and tracking your satellites. This can be a really big issue if you're a satellite operator that's tracking hundreds or thousands of satellites, Starlink, for example. Also, energetic electrons from these geomagnetic events may become trapped in radiation belts, causing electrostatic charging on the surfaces of these satellites. However, the latter of those effects, the energetic electrons, those effects are relatively well characterized. So satellite operators know the radiation environments in the different altitudes in which they're operating their satellites. So complete satellite losses are rare. However, these neutral density changes are still being modeled. The models, are not perfect. They're always evolving. So that's a big area where we need to improve. And just as an example, this is probably the most infamous of them, but in February 2022, Starlink lost 40 satellites due to relatively minor space weather. So essentially the story goes is that there was a CME impact. We reached G1 or KP5 levels, nothing major there. And then once those conditions subsided, SpaceX said, okay, we've met our criteria, we're gonna launch our Starlink satellites. But what they didn't know is that there was another CME on the heels of the first one. So they launched their Starlink satellites, and then the thermosphere expanded due to this new geomagnetic storm, and then all the satellites deorbited. So will this happen again to Starlink? Probably not. I think they've learned their lesson after losing 40 satellites, but it's not just Starlink that's launching huge clusters and constellations of satellites. There's more and more companies, more and more organizations planning on launching tens or hundreds of these objects into space. So this isn't to say that this will be the last time we see something like this. Humans are working in the atmosphere. We have airline pilots, crew, and frequent flyers. High energy charged particles are constantly bombarding the Earth. Those are cosmic rays, but these high energy particles become enhanced during radiation events. So particle fluxes are the highest at high latitudes and altitudes. In extreme cases, crew dose limits are reached and polar flights have to be rerouted. So here's an example during the Gannon storm, May 11th. You can see the green line is a normal routing for this Qatar Airways flight, but due to the extreme radiation, they actually moved it down to a lower latitude. So luckily, these events are mitigated. Humans are also working in space. In geospace, humans lose the protection of the atmosphere from radiation and receive higher dosages. But in interplanetary space, they lose the protection from the magnetic field. So this is a big problem for crewed flights to Mars and the moon, is how we're going to manage these dose rates. And we've heard yesterday that during the May storms, if you were on the surface of Mars, you would have received 30 chest X-rays as a radiation dose from those events. Not good. So single event upsets are relatively simple. It's when ionizing radiation changes the internal voltages in electronics. This can corrupt stored or transmitted data, and this affects electronics at all altitudes, including avionics. So almost all commercial aircraft have error correcting mechanisms now. Part of that was due to an event that occurred in 2007 where a Qantas airline actually crashed due to an SEU. So these have been deadly in the past. During the 2003 Halloween storms, 10% of satellites experienced these single event upsets, 1 was completely lost, and 10 were non-operational for over 24 hours. So here are 4 years on the screen. I'm sure everyone knows what these mean, but in case you're not aware, these are years where we had very extreme space weather. So in 1859, we had the Carrington event. That's the famous drawing from Richard Carrington of the Sunspot Group. March 1989, we had a very significant event where we had transformers melting down and millions of people across Canada losing power. The Halloween storms, of course, very recent, and those caused a lot of issues with satellites. And then just a few months ago, the Gannon storm in May. And you can see the auroral oval there expanded to very low latitudes. But what's also different about these years, besides them being, different years and centuries apart, is that we had very different technology during those times. So the impacts were very different. In 1859, right, we only had really telegraph systems. And if you've read the newspaper reports, you'll know that a lot of these stations completely burned down. So not very resilient, but we also didn't really know much about space weather at that time. In 2024, we have a lot more going on. We have satellites now transmitting internet from space. We have 5G being beamed down. We have airlines that are getting rid of a lot of the manual VORs, sort of these analog systems in favor for relying on satellites for positioning, high precision farming, drone deliveries. GPS is used in essentially everything and is relatively susceptible to space weather. So how are we going to deal with all this? Space weather is impacting us more than ever. Here's just a quick example showing the SWPC Space Weather Prediction Center product subscription service growth as a function of sunspot numbers. So this is the hard data showing that more people are paying attention to space weather than ever before. And solar maximum is here. So like we saw in the last talk, it doesn't take a really strong cycle to get a Carrington event. And this cycle is nowhere near over. We just recorded the highest sunspot number monthly average since 2001. And today on the sun, we had 270 spots, which is the highest it's ever been. So, the solar cycle's here, it's not messing around, and we could see extreme activity in the coming years. So it's important that we have these discussions about how we're going to be prepared and how we're going to make ourselves resilient to space weather. So this is kind of the motivation, is increasing reliance on technology makes modern day society more vulnerable than ever to space weather impacts. And these grand challenges that we've been hearing about throughout the last couple of days require new approaches and ways of doing science. So what if we saw a Carrington level event this solar cycle? What would happen? What do you think? So here are some grand challenges in heliophysics. I actually pulled this from a slide at COSPAR, which I was at a few weeks ago. I'm not an expert in all these questions, but one that I really think I can speak to is the coupling between the magnetosphere, ionosphere, and thermosphere systems. So, this is one that requires a lot of cross-disciplinary efforts and, working between communities to answer these questions. So a risk and resiliency framework is one way to approach this. Of course, there's many different ways, you can look at this problem of increasing technology in a society more vulnerable to space weather. There's multiple ways you can solve this or, attempt to solve this, but the one that we thought of, which was very appropriate, was this risk and resiliency framework. So really the motivation here, again, is that space weather is complex. We need new ways to approach the system to understand what is needed. A key attribute of this risk and resiliency framework is a consideration of not only the sun to society, but also the sun to mud system. So space weather starts in the sun, but it doesn't end when you leave the corona. It doesn't end when you leave the surface, right? It goes all the way down to the ground on Earth. So evaluating a system within this framework is asking the question, how can the system accommodate changes and reorganize itself while maintaining its unique characteristics? In other words, how are we going to bounce back from a Carrington event or an extreme space weather event? So here's the Heliophysics System Observatory, essentially all the missions being flown right now, plus or minus a few, because this is from 2022. But this sort of puts everything in a different frame of mind. Is you have all these missions, you have all these data sources and different streams here, and this risk and resiliency framework really involves all 4 of these steps. So integrating systems level information across the sun to the Earth, assessing the probability of space weather activity and storms, assessing the vulnerability and resilience of our society to these impacts, and then determining the socio and economic outcomes there. So these are, further diving in, 4 improvements that we can make to achieve this resiliency to space weather. So making our science open and looking at data science principles, information systems, cross-disciplinary science and international collaborations, and also citizen science. And together, this can make our world more resilient to space weather. So open science and data science, of course, the amount of data in space weather is increasing. This is no surprise to people. We're flying more satellites than ever, and we're recording terabytes instead of megabytes of data. So we're dealing with data all the way from the surface of the sun to the surface of the Earth. So this really spans multiple fields from solar physics to geology. Part of this data science principle, so data science is, of course, a very broad term, broad topic, in also applying to space weather. But open science is one that we can focus on. So that means making your science available, free to use, standardizing the metadata, making your semantics, basically having a unified semantics in your data, making them easily findable, accessible, interoperable, and reusable. That's the FAIR data use principles. So in other words, democratizing the science reduces the barrier to research. And this also helps fix the pipeline problem. You may have heard of this, but essentially it's the issue in our field that we're facing, that more people are retiring or leaving the field than replacing. So this is a big issue. And one way we can help combat that is making our science open and allowing people who may not have the resources to get started. Maybe they're not in an institution that has a really strong space physics program. That was me in undergrad. There were no faculty that were doing space physics, so I really had to seek out these opportunities on my own. This could help a lot of those people. And one example of science being open is that in the US now and NASA, all the data are made Creative Commons 0, so that's the standard of fully open data. And a really good paper to sort of illustrate the data science applied to space weather is this McGranahan et al. 2021, where they have a figure showing sort of a data web of basically all the principles of data science that fit in here. So, I talked about making science open, but there's also the collection of the data. There are certain principles and standards you can apply there. There's managing and communicating the data as well. And of course, there's analyzing the data. So this is just sort of a network of data science topics. Cross-disciplinary science is really doing science between fields. So not only between the different fields in space weather, for example, solar, magnetosphere, ionosphere, and GIC, but also communicating between different stakeholders in the space weather enterprise, whether that be theorists, modelers, forecasters, or industry. The information flow should be bidirectional, meaning that it shouldn't just be from the scientists down to the forecasters, down to the industry. Industry should be telling scientists and modelers what they really need. Maybe it's just volts per kilometer, right? So this communication improves trust between the different users. It also avoids duplicative efforts. And the goal, again, is to develop this system science approach to space weather. So this is my favorite analogy, is sort of using this, it's like a cartoon, basically, of showing an elephant and all these scientists looking at the elephant and concluding different things. So none of them realize what they're looking at is an elephant, but you see one's looking at the tusks and saying it's a spear. The other one's looking at the tail and saying it's a rope. And none of them realize, oh, we're actually just looking at the same thing. I think that's kind of similar to space weather in a lot of ways, as we get really siloed in our communities and really ingrained in our own research that we may lose light of the broader context, right? A CME doesn't just start on the sun and then it's gone, right? It eventually propagates out in interplanetary space, hits the magnetosphere, tons of interactions go on. All those are separate fields, but they're all connected. It's all space weather. And we can do cross-disciplinary science today, not only within our field, but at IAU, it's a great opportunity to connect with other people from other disciplines of astrophysics, not just heliophysics. And I've had some conversations already with people studying black holes about how they're using different MHD models and how that compares to things in the magnetosphere like Gamera, and it's been really cool. So, this is a great opportunity to connect with one another in this room, but also explore out to other fields and see what's going on. Information systems are ways that we can achieve cross-disciplinary science and open science in space weather. In other words, they're technologies that provide the structure to collect, store, process, and integrate data. So they're ways that we can do and coordinate collaboration to improve our scientific knowledge and accelerate scientific discovery. And they're really applied things. So there's these are just some examples. There's more in this Masson et al. 2024 paper. But HelioCloud, Space Weather Trek, the ESA Data Labs, Komodo, which is a Python extension developed by the CCMC at NASA, the NSF EarthCube AmGeo project, which connects a bunch of NSF-funded facility data sets together like SuperDarn. There's tons of these information systems out here that I think should be realized and leveraged a bit more so we can connect different data sets together and realize these system science approaches. International collaboration, of course, is important, and we're here at the IAU, so it's a great time to do that. But, you know, of course, space weather events create global impacts on regional scales, right? I think this is lost a lot of the times, is that once it hits Earth, it's not over. It doesn't just affect the world in the same way. For example, in the United States, we have far different effects than people in Brazil or even in Africa, for example. Equatorial areas versus areas in mid latitudes or under the auroral ovals will experience very different impacts. So fostering international collaboration requires this open science approach. Finally, citizen science. This is my bread and butter. So the definition is that organized research in which members of the public engage in the processes of scientific investigations by asking questions, collecting data, and/or interpreting results. And this slide shows all the different ways that citizen science can look. You have people in the classroom, you have scientists collaborating with students and educators, you have people interacting with citizen science projects, you know, either at home or in the field, literally taking photos of plants, for example. So citizen science is not just heliophysics, it spans all of science. It's a very powerful tool that I think needs more attention. In heliophysics, there are really two kinds. There's direct collaboration with individuals, for example, sourcing photos from aurora chasers to do research. There's also project-facilitated citizen science. So this is not only a way to do research, it can actually be more efficient and yield better results than, for example, training an ML or AI algorithm to look for spikes in time series of data. That's a lot of our work, right? It can be better than doing that. It's also a conduit for public education and outreach. So we're in solar maximum, the public is paying more attention to space rather than ever before. This is a professional, formal way of getting the right information out there to people. So just on the right is one example. Recently, we released a preprint where we investigated citizen science reports of aurora during the Gannon storms. And as you can see, actually the aurora was further south than all the professional scientific grade all sky imagers. So we studied the aurora chasers reports and came up with some really interesting conclusions about what the aurora was doing during that event. Here are just some recent aurora citizen science discoveries. I'm not going to go into everything here, but aurora chasing is really pioneering the field. Collaborating with scientists, we're actually making headway on that grand challenge question of how the magnetosphere, ionosphere, and thermosphere couple together. So this is just one example directly showing that citizen science is working, essentially. We can also build communities and do research through more formalized citizen science projects. Here's just a snapshot of all the different citizen science projects underneath the NASA umbrella. And just to conclude here, space weather poses daily risks to technology and life, right? We're a lot more advanced than we were in 1859, and we're becoming increasingly vulnerable every single year. We need to recontextualize space weather in a risk and resiliency framework. This is just one way of doing things, but I think it really sums up everything nicely, is that we need to approach things from a system science perspective. In order to solve these grand challenges in heliophysics and make our society more space weather ready, really we should be doing these four things: is make science open and accessible, emphasize cross-disciplinary efforts and information systems that help coordinate collaboration, work together across nations, and of course, believe in citizen science. Thank you.
Yeah, thank you very much for this talk. Are there questions? Any questions?
I have a quick question. Can you hear me?
To be the case, so we all have a couple of minutes before the poster session starts. Gives us time to go down and
I have a question.
Tea, coffee, whatever. So thank you very much again.
Oh, cool.
Okay. Okay. Oh, virtual people. Okay, I see. Okay. Okay. Do I have the nod to start? Do I have the nod to start? I can start now. Do I? Okay. Good afternoon, everyone. My name is Nondumiso Kumalo, and I am a space weather forecaster from the South African National Space Agency. So allow me today to give you my presentation titled Santa's ICAO Connection and its effort in space weather radiation research. And I'd like to give credit to Santa researcher, Dr. Rindani Ndanganini, who I'm standing in her place today, presenting this on her behalf. So if you would have any queries from this presentation, do look at that email that I just put there on the slide. How do I go next? How do I go next? How do I go next? Oh, I thought this was just a picture. Okay, thank you. Okay, so I'm just gonna give you a definition of what space weather is. I'm pretty sure, as Vincent in his last presentation mentioned, most of you are familiar now of the term space weather, but I'll just mention it for formalities. So space weather refers to the conditions on the sun, in the solar wind, the magnetosphere, the thermosphere, the ionosphere, and how these can influence the performance and reliability of our spaceborne and ground-based technological system. So not delving further into this, but we have what we call our space lab. So because space weather focuses on what is happening on the sun and how it eventually affects us here on Earth, we focus on that 1 AU distance between the sun and the Earth, which we refer to as our space lab. So it's called a space lab because it's what we use to study space weather. Again, an image which is now familiar to you, even from the previous talk. I'm just going to mention the importance of having a multi-point view of the sun. So of course now we can't go into space, right, physically. So for that reason, for us to study this region of the space lab, we need to have some satellites or instrumentation which are doing the observation on our behalf in that space. So of course we have several satellites that are currently in orbit that are measuring these parameters in the interplanetary field, in the interplanetary media, as well as near the sun, like the solar orbiter that was mentioned in the previous few talks, as well as some which do in situ measurements such as ACE, Discover,
And I'm very familiar about the data from the satellites because, as I mentioned, I'm a space weather forecaster. So satellites such as SOHO let us see the eruptions as they come off the sun, right? So they're very important for us to have our eye on the sun and to see these eruptions as they leave. Because if we didn't have these satellites, we'll be moving about blindly. So it just points to the importance of having such satellites collecting these data for us. So I'm just going to speak on a few points which were mentioned again. This is going to be very repetitive because it was mentioned before as well. So having this multi-viewpoint view of the sun, it allows us to have an integrated system level information across the sun to the earth. Of course, as I mentioned, the satellites act as our eye in the sky, so allowing us to see what is happening on the sun and eventually predict how these events will impact us here on Earth. So something else that goes into my space weather forecasting. So having our eye in the sky helps us assess the probability of the space weather activity or the storms. So then we are able to see these events as they happen on the sun and eventually how they can affect us here on Earth. And of course, assessing the vulnerability as well as the resilience of some systems that may be affected by space, as was mentioned again earlier. So of course, now that we know that space weather is detrimental to our technology, we'd want to also have an idea of how vulnerable or how resilient are we to these events. And of course, determine the socioeconomic impact. Well, all of us would want to know, how does space weather affect me on a day-to-day basis, right? Space weather impacts. So delving further into that, this is just a nice figure diagram showing us what happens from the time we have something happening on the sun to the time it eventually impacts us. So as mentioned various times, we have one of my favorites are coronal mass ejections as well as solar flares. So coronal mass ejections, as was mentioned, these are eruptive plasma from the sun that when they are directed towards Earth, they get to bombard our magnetic field and cause what we call geomagnetic storms. And as was mentioned as well, so we know that the change in the magnetic field can induce currents, right? And one of the things that can be affected on Earth are what we call power grids. So we get what we call geomagnetically induced currents, right? These are just a few amongst many impacts that results from space weather. And another one of my favorites is solar flares, the bursts of radiation that come from the sun. So we know these ionize our upper layer, our upper atmosphere, called the ionosphere. And this can in turn affect our high frequency communication, which we use for communicating in the radio frequencies. The table next to that figure or diagram, it really is similar to the one next to it, but you can see here I just outlined the two first rows, because later on I'd like to focus more on radiation and how it affects the aviation industry. We can see that some events such as the solar energetic particles, they pose a risk on passengers and crew on flights, high altitude flights, as well as, of course, on avionics, which are the electronics which are on board a plane. Now, coming closer to home now. So SANSA's journey to becoming an ICAO designated space weather center. I'm not sure if you are familiar, but in 2017, ICAO issued out state letters to all the states requesting as an invitation, inviting the states to host space weather centers, right? And it was later on, they implemented some of the standards and recommended practices in one of their ICAO documents. So ICAO now realized the importance of space weather on aviation, and this prompted them to include the space weather information into their flight plans. So in 2018, the following year, the successful states that responded to that that invitation rather, were announced. And I'll show the results in the following slide. Okay. So these selected centers were grouped into two. First, it was the global centers, and next it was the regional centers. So initially, we had three. So the first one is the ACFJ consortium, which comprises of countries such as Australia, Canada, France, and Japan. The next global center, also comprising of various countries, it's referred to as Pegasus, comprising of countries like Austria, Belgium, Cyprus, Finland, Germany, Italy, Poland, Netherlands, and the UK. And the UK, it's through the Moswak Space Weather Center that they have there. And of course, the United States, which is hosts the global center through their Space Weather Prediction Center in Boulder. And the second group is what we refer to as regional centers. So initially, we had two regional centers. That is, it comprised of various countries, again, China and Russia Federation Consortium. But later on, these countries bidded to be converted from a regional center to a global center, and their bid was accepted, and they now converted to a global center. So I think all in all, now we have 4 global centers. And the second, now the only regional center that we have is the one that we have here in South Africa, just an hour and a half away in a small town called Hermanus, where I'm coming from. So South Africa is hosting the regional center from there through center being designated by the International Civil Aviation Organization. So what were the requirements for these states, right? I guess ICAO had to have had requirements from the states that were selected. So some of these were to monitor the relevant ground-based, airborne and space-based observation, to detect and predict the existence and extent of space weather conditions that impacts the following main areas, which comprise of high-frequency communication, satellite communication, global navigation system-based navigation and surveillance, and of course, radiation exposure at flight levels. So you would see here that these are the main things that aviation focuses on and which are affected by space weather. So it's very imperative that the aviation industries know about these or have information with regards to these. And of course, they had the task of issuing advisory information. So under severe or moderate storm conditions or severe or moderate storm space weather conditions, these centers had to issue advisories to to the relevant aviation channels, as the next point points out. And of course, maintaining a 24-hour watch, because we know the sun never sleeps, right? Space weather is always happening. So it's very important, again, that we always keep an eye out for what is happening up there. And of course, to ensure active collaboration with other regional centers and the global centers to ensure a continuity of information, because we should always be ever learning, especially in this new field of space weather. Right. So now coming back to us, after being designated a regional space weather center at SANSA, we had to make some few changes, of course, because now we have to adapt to new changes, because before we were just operating 9 to 5 normally, but now we had to have a 24/7 operational center. So we did build a capacity. One of them being that we had a new space weather center building that was built and was completed and officially opened for 24/7 operations in November 2022. You can see it's such a beautiful building there in the middle image. This is an image taken in the night. Yeah, and at the top there you see our view wall display, which is the screen we look at to monitor the conditions in space and be able to forecast what might happen from the sun. Okay. And just below that, you have my team. So this is the space with the team. And in the middle here, I should use my pointer. Here is our head of space weather, Dr. Mpo Chisapungo. And around her are the rest of the forecasters. We recently have 3 new forecasters which were introduced into our team. They are currently undergoing training and will soon be integrated into the 24/7 operation. So of course, with having this building, we had to also incorporate some new ICT architecture, because of course, with this display, looking at the sun on a 24/7 basis, we need some high-tech ICT architecture. And of course, with the skills, capacity, and capability, that's where we fall in as the human capital, because we need to be there to monitor space weather and to study it. Okay. And one of Santa's posts is that of an African instrumentation network. So we have several GNSS receivers that are allocated in different parts of Africa, different countries, where we get to read vertical tech as well as scintillation from these stations. And few of them are located in countries such as Nigeria, Zimbabwe, Namibia, etc. Those are just a few I'm mentioning. Okay. Now, space weather radiation research. So part of ICAO decision to include space weather information into its planning, and the task that they had to give the space weather centers to issue advisories. Of course, if you would issue advisories on an event, you should have certain thresholds. Oops. You should have certain thresholds where you must know that if these thresholds are exceeded, this is where you send the warnings. So we have for different things like GNSS, radiation, and high frequency communication, but I'll focus mainly on the radiation part, especially because this is very important for ICAO and for passengers and crew. So when you have a radiation dose of 30 microsieverts per hour, that is considered as a moderate condition. And then at greater than 80 microsieverts and above is considered a severe warning, okay, or a severe event. Okay. So I think we all know that most particles enter our Earth's magnetic field through the poles. So most of the exposure is expected to be in the high latitudinal regions, as very much shown in this plot. No. Oops. Okay, I can go back. Okay, as shown in this lovely image here, where most of the radiation, the microsieverts per hour, is observed in the northern part of the globe, as well as the far southern part of the globe. And in the equatorial regions, this is where there's maximum shielding from this radiation. So this figure here is just, or graph rather, is just emphasizing the various contributors to cosmic radiation at different altitudes. So I know that the cruising altitude, or the cruising altitude is usually between 10 to 15 kilometers. So at that point, usually we have the main contributors to radiation being, the neutrons, as well as the electrons or photons, followed by the yellow, which, okay. Yes, okay. So it's the protons, the neutrons, and the electrons, and the photons as well. Okay. In 2003, the FAA, which is the Federal Aviation Administration, which is in the US, issued its first ever alert on radiation doses on by passengers, airline passengers above 25,000 feet. So this was the first time an organization took the initiative to actually issue out a warning on these doses. And I think as a result of this, some flights were deviated from the normal polar regions, and they had to avoid such exposure upon their passengers and crew. And as you can see here, as much as it was only the US that issued that portion to their aviation industry, you can see that most of the places, Europe mostly, and even us here in South Africa, we were supposed to issue warnings on this irradiation exposure, but unfortunately, then ICAO hadn't required space weather information to be part of flight plans globally. And just as a cause of that, that was during the October 2003 storm, where we had a lot of activity. I think that was when we had the Halloween storm as well, where we had the flare reaching an extreme X24 and followed soon after by another extreme one, an X14, resulting in an increase off the charts exposure to proton flux. So at SANSA, we do make efforts to delve further into the radiation exposure. And one of the projects that was undertaken was between SANSA and the Northwest University, where a balloon was launched. Oopsie daisy. Where a balloon was launched by a student. So this is a paper from a student. They launched their balloon from the Northwest University in Potchefstroom, and it went and landed eventually in Orangeville. So this just shows the trajectory of the balloon here in blue and the flight path predictor. So initially they had predicted that this is the route that the balloon would take, but it actually took this route and ended up here. So this is just another, is it? Okay, thank you. Okay, so yes, this is just a summary of the count per minute of the radiation that that balloon measured, as well as how the pressure and temperature changed with time. Okay. This is another instrumentation, which is really fascinating. It was, I think, developed by some students, I think at the Northwest University as well. It's called the High Altitude Radiation Monitor. So some of our researchers, like Dr. Rendani Ndanganeni, she usually carries this instrument upon being allowed, of course, on the flights, international flights. And you can see some of the parts that were taken. Oopsie. Oops. Some of the flights that were taken from here in South Africa, like Cape Town or Tambo in Johannesburg, some going to Addis Ababa, and some going to Frankfurt in Germany. And of course, this is what that dosimeter measured. So for the part going from South Africa to Germany, this is the time where the plane will be taxiing. And of course, as it ascends, you get the radiation dose rising. And you can see as we're getting closer and closer to our destination, which is Germany in the higher latitudes, you get the doses increasing. And eventually the flight, of course, comes back down to Earth and radiation doses go back to background levels. And this is the part from South Africa to Ethiopia. It's slightly different, similar, but slightly different. Mainly because of this dip here. Of course, I did mention in the equatorial part of the globe, that's where we get the maximum shielding from radiation. So of course, it dropped at that point. Okay. So in summary, the multi-point view of the sun is crucial in allowing for a better understanding of the Sun-Earth environment and developing improved forecasting methods. Space weather poses a risk on passengers and crew, especially from radiation exposure, as well as avionics. hence why ICAO recommended that the practice for space weather information to be included in flights plans. ICAO's role was to designate global and regional space weather centers that will monitor and issue space weather advisories when necessary. And South Africa, through SENSA, was designated as a space weather warning center for Africa. And of course, in closing, SENSA continues, there's continuous efforts that is being made by SENSA in collaboration with other South African universities and research institutions to undertake radiation exposure research. Thank you so much. I think I did. Yeah. Okay. Yes. Yes.
Very nice talk. Thank you. Is this working? You said that the building was built in 2022, right? So, and you have people training right now. How far are you from sort of full capacity operating as proposed and all that?
Okay, sorry, maybe I didn't phrase it correctly, but in November 22, that was the official launch of the building. So prior to that, we had started 24/7 operations earlier in August 2022, but that in November, it was the official launch. So I think the building was started in 2021. So it just was over a year where it was completed. And in terms of the capacity, yes, now it's fully 24/7 operational. We work on a 24/7 basis. Even now, you'll find a forecaster. Even at nights, we are there monitoring. So we are full. I think the additional forecasters that I mentioned that are currently under training, it almost like it's just to relieve the burden of maybe working more than we should. Yeah, just building more capacity, because I think because before they came, there was only just, how many, 8 of us. So, and that caused a strain into like schedules and everything like that. So we knew that we had to have more manpower. But in terms of the Space Weather Center operating continuously on a 24/7 basis, yes, that is complete.
That's great.
Thank you so much.
Thank you for your excellent talk. And I have a question. So do you have any research about the SAA? Because they are reasonable about SAA radiation or particle or something.
Do I have? Please repeat.
SAA. SAA. Southern.
Unfortunately, I'm not too familiar about that, but I did mention, unless someone else in the room has an idea. Unless, yeah. Okay. Okay, yes.
So yes, the question was about the SAA, the South Atlantic Anomaly, and we do have one of the other one of the other forecasters is also doing research on her master's, and there are some other students as well who are studying the properties of the SAA and its change over time and so on. So the answer is yes, at a low level.
Thank you.
All right. If there are no further questions, let's thank the speaker again.
I had a question on the chat.
Okay. Good afternoon. Okay, thank you, Chair. I'm Chao Song, come from the National Center for Space Weather, China Meteorological Administration, and I will give you a talk about the analysis of Henan Hao and the impact on the space weather, based on our Fengyun satellite data. And so first of all, the introduction to the Fengyun satellite, and then followed by the application and the preliminary result and the summary. So we all know the sun. Maybe the most astronomers think the sun is an ordinary star, but it's our star. So it has a very important influence to our planet Earth, especially the weather and the space weather. No, so many satellites work on to monitor our sun, and the Fengyun satellite is also among of this satellite. And the Fengyun satellite is Chinese meteorological satellite, and the Fengyun is actually two words. Feng is mean wind, and Yun is mean cloud. And it's a big family of satellite. For the polar orbiting satellite, including Fengyun 1 A, B, C, D, and Fengyun 3 A, B, C, D, and so on. And this is the polar orbiting. And the other one is the geostationary satellite, is around there, and including Fengyun 2 A, B, C, D, and so on, and the Fengyun 4A and the 4B. This is the new generation. And the Fengyun satellite also carry a space weather instrument, such as the solar X-ray and the UV imager. And this is the composing of this instrument. We have the two telescopes for the trace guide and the radiation sensor, and the X-ray and the UV complicated velocity. And this is the parameter of this instrument. We have X-ray channel and UV channel. And this is the observation of the XUVI. This yellow one is for the UV image, and the right one is the X-ray image, and this is the measure from the sensor. And so this XUVI also has the research application, and first, especially for the solar UV wave. And this is the multi-point observation of our sun. You can see this column is the XUVI. You see the wave, the font of the wave is purple ground. And we cut a slice and can measure the velocity and so on for this UV wave event. And we also develop a method, because this image of the XUVI has a rotation. We use the rotation to develop a new flat field correction method. And this is before and after the correction. And this is a combination between the Fengyun UV and the SDO-AIA image. So the XUVI image also can be used to study the trigger process of an X-class flare from a small active region and a double-dick filament.
and the image super resolution measure, and to find out the solar orange of a strong geomagnetic storm. And because the sun is the main source of space weather, so we must monitor it. And this is the solar disk from the XUVA, and we can see a active region, and this an X class M class flare from erupt from this AR, and you can see the bright and the dimming. And the major flare may impact on our XF radio and navigation system. And the other important arm is the coronal hole. We know the coronal hole is a dark area in the UV image, and they have low density and low temperature. And the high-speed stream solar wind from this coronal hole might cause the geometric storm, and they because they catch us the slow solar wind and the formation the congregated reason CIR, and so a lot of CIR may associated with the geometric storm. So we forecasters are often concerned about this. Especially the low latitude coronal hole, because they might have the major geometric effect on our Earth. And this is the advantage from the low latitude hole, the coronal hole. And you can see the dark region on the UV image. And we also see the PSF model to confirm they have the open light. You can see the blue light from this dark area means a large scale open magnetic field. So this is actually a low altitude the coronal hole, but we saw the geometric field we don't find any geometric storm or even actual active condition from this. So this is quite coronal hole. And the other case is also a low latitude coronal hole, basically in the same position. And this time they have some company, the coronal mass ejection, and you can see the two one and the red one may be a partial halo CME, and with this CHSS and the partial halo CME, they all work together to create a strong magnetic storm. And we can say the interplanet magnetic field has a strong magnetic field. You can say maybe 40. And so the summary, by using the XUVA image, we analyze the low altitude coronal hole with the influence and the interaction between the CME and the high-speed stream from the low altitude coronal hole might be led through the geometric storm. And there are a considerable number of the low altitude coronal hole that did not cause the geometric storm. Yeah, so the space weather forecasting may need to pay attention to this full positive and the full negative caused by the coronal hole and the tsunami. And in the end, have a little add for our center. So our center is the National Center for Space Weather. We provide the daily forecast and weekly, monthly report for the space weather. And we also are part of the CRC. Is one of the 4 global center for the International Civil Navigation Organization. Oh, and this is our website. This is our building in Beijing, and welcome to visit to our center. And that's all. Thank you.
Yes, I have a question. So this constellation of satellites is in polar orbits. So you'll get you have to share the mic, sorry.
Okay.
So your constellation of satellites are primarily in polar orbits, whereas the US satellites are in geostationary orbit. So do you try and does that help models of the particle fluxes to have satellites in very different orbits, or is that an area of future research? Is it?
Okay.
Do you use the information from both sets of satellites, or that's something that might be a future? So I was just asking if you also look at the data from the American satellites to model the difference in particle fluxes and so on that you talked about, or is that so if you show your the orbits, maybe it's not an important question. Yeah. But there's many space weather satellites now, and perhaps cooperation in the future to coordinate between all of these, and as well as other satellites in geostationary orbit could be an area to explore.
So the other.
I guess you also have to use the mic.
Okay. The other phone-in satellite also carry out the different the space weather adjustment also for the X-ray flux or the particle. Yeah, we have particle and the geometric field for the geometric field in the satellite. Yeah, we also we are carry the multiple entrustment from the satellite. Okay. Oh yeah.
Yeah. If possible, I have one comment. And the first thing is how about the Fengyun 3E data publications? That means we can free download to the global or need to register and download. This is the first comment. Second comment is the Fengyun 3E. Is there any special data for high-vol and high-vol particles data?
Yeah. So because it's space weather is a global thing from all the human beings. So we are working on our data and for the collaboration. Yeah. So yeah.
Yeah. Thank you. Thank you.
Yeah. Thank you. Yeah.
Tell us about the ionosphere, right?
Yes.
Okay. Okay, thank you very much. My name is Chimangazo Matamba. I'm from South African National Space Agency, and then the work that I'm going to present is in collaboration with Dr. Donald Dunskin. So my topic is about the effects of space weather on the Earth ionosphere. So this is just the outline of my talk, which I will just pass. So like at the past or like two talks, like they've described about what space weather is. So I will also just skip this slide because they've already introduced it to us. Then what is the ionosphere? So the ionosphere is the region that extends from about 50 kilometers to about 1,000 kilometers above the Earth's surface. And then the ionosphere is formed during the interaction of electrons and protons during extreme ultraviolet radiation. And then the ionosphere changes, like it's not stable, so it varies with like time of the day, it varies with season, it varies like also during geomagnetic activities. So like the ionosphere, like during the day, it has like four main regions. The first one is like the D region, the E region, F1 region, and F2 region during the daytime. But at night, the F1 and F2 region, they combine to form the FR region. And then like we are left with a F and E layer. So in this cartoon here, I'm not sure which button to press to get a pointer. The small one, oh, this one, okay, thank you. So in this cartoon here, you can see like we have the solid line here, like representing the electron density. So this is during solar maximum, and then the dashed line is representing like during solar minimum. So you can see during solar maximum, we have like high electron density in comparison with the solar minimum during the daytime and the nighttime. As also I've mentioned, the ionosphere also varies with like a geomagnetic or geographical latitude. So this image here, like you can see, it's written like the layers here. You can see the auroral region, the transition region, the mid-latitude region, and then the equatorial latitude region, and then you also have a mid-latitude also on the northern hemisphere. So like in this image here, it's the same as the bottom one. So this was taken around, I think 23:05 UT. And then like in South Africa, it was nighttime. So you can see during the night, we have a low TEC values. And then you can see from this color bar. But in this other region, you can see enhanced TEC values, especially over the equatorial latitude region. So in this region, you can see also they've also put the sun here just to show that it was date side. And then this image here, it's taken around 10 UT, which in like in South Africa or Africa, like it's a day side. Then you can see we also observed the high total electron content over the equator. As I've already mentioned, so this cartoon here is just showing the layers of the ionosphere and then where they are, and then you can also see that it varies with at the time of the day. This slide. So here, like the total electron content is defined as like the line integral of a free electron from the receiver, from the satellite and the receiver, and then it's given by this expression here. And then here, I just showed some stations that we are monitoring or that we are using for our near real-time TEC product. As you heard the previous presenter, Nondumiso, talking about the total electron content maps that we have at South African National Space Agency. So these are some of the stations that were used also for this analysis, for this presentation. So this is the paper about the development and evaluation of our near real-time tech product and other products for space weather or for space weather in Hermanas or at SANSA that was published, like which has the methodology on how we calculated the TEC products and other products that we have. And then this is the paper that I'll be presenting about. So here we have chosen like the storm condition that happened in 2021 in November. So this was the largest storm that we saw in November 2021. So this event just coincided with like the time when we wanted to submit the paper for our development of the products. But then here it's showing the planetary K index here in different threshold. So like the green one is just KP less than 5, and then the orange one is showing G2 or G3, and then like the yellow one here is showing like the G1. And then here, like we also overplotted the DST index, and then you can see like on the third here, you had like a sudden storm commencement, and then like you have the storm like main phase or like the minimum DST on the fourth here. And then as you go, you also have some substorms that like followed this storm on the 5th and then on the 6th and so on. So here I just showed the severity of the storm, like when we are using DST. So the weak storm is defined as a threat from -30 to about -50 nanotesla, and then up from -100 to 200 nanotesla is considered as a strong storm. And also for KP, -7 nanotesla is considered as a strong storm. So here, like in this analysis, we have observed a strong storm that has started from on the 3rd. So these black lines that we have just pointed out, like is the time when we get like some measurements from the global ultraviolet maps. So I will explain when we get to those slides. In this slide, just showing like the total electron content, like a diurnal plots. So these measurements are like from Hermanas station. So Hermanas is found right here, like in Africa. So I just put this map so that you can see like where we are. And then like here, these measurements, the black ones, like they were extracted from our TEC map, like the near real-time TEC map. Every 5 minutes we get like a plot, then we extract a value around that time. So for the Hermana station, like you can see on the 3rd, on the 4th here, like you can see a decrease in TEC. So like maybe before, like the red one is just showing the median of TEC. And then the green and then the shaded region is just the plus and minus like standard deviation of for that month, for the monthly median. So like when you see these black lines here, you can see they are below even the standard deviation, and then which shows like a depletion around this time. And then also on the 5th, you can see like the TEC values like were depleted like twice like what we expect to see on this day. And then you can clearly see here, and then on the 6th, you see it start to recover, to go back to normal. And then these observations that we are seeing here, you can also clearly see them here on the delta TEC values. And then if you can look like on this, so you can look on this curve here, it looked a little bit smoother, but you will see when we get to the next one. So this is Grahamstown station. So Grahamstown is like around here on the map. Hermanas is on this side, on the west side, and then Grahamstown is on the east side. And then like you can see here, like during that time of the storm, like for Grahamstown station, you can see there were a lot of fluctuations during the storm, and also we have observed a decrease in tech, but there were more fluctuations in comparison with the previous one. Then here we extracted some like some maps from like the ones that I showed, the lines on the DST and KP index at that particular time. So for each day, so this is from the 3rd and then 4th, 5th, and then the 6th. So like as I've mentioned, the ionosphere varies with time of the day. So during the day, like we expect to see like high TC values, and then during the night we see low TC values, like as you have seen in the previous map, like when I was still explaining about the ionosphere. So in this case, this is what we expected to see, like for each day of this of November. Then, like this is sorry. So this plot, like these dots that you're seeing overplotted, is just the TEC at IPP, and then like the background one is like a gridded tech values that we have done some interpolation, but this is what you are seeing. And then on the fourth here, you can see we have observed the low TC values around the southern part, and then on the northern part, we observe the high TC values. But the values that we have observed here, they are similar to the ones that we are seeing around here. But we saw the enhanced TEC around the northern hemisphere. And then on the fifth, that's where we have observed the depletion, like which was double. And then you can see here, we have like a decrease in tech. But what is interesting here, you can see we have two shades in this graph. We have like on the west side, it's like it's light, which looks like maybe like day side or like which is high TEC. But on the east side, we have like the blue blue shade, which is very low. And then what we expect is because the sun like comes from the east, we expect this side maybe to be more enhanced in comparison with the west side. But here we are seeing the difference. So this was just the impact of the storm like that we are observing here. So on the last day, we can see that everything has recovered, it's starting to go back to normal. And then here on this plot again, you can see like the change. We have a gradient, a big gradient here going up. And then the Grahamstown station that I've showed you, it's around here. So that is why like we had more fluctuations over Grahamstown. And then the next one is just to show the tech gradient based on the previous tech maps. And then the big gradient that we have observed is it was like when we had the enhancement, like here you can see going from east to west. And then also the one that I've showed you, like we also had it here. And then the Grahamstown station is just located here. So that is why we had more fluctuation. So there's the decrease in TEC. We thought it might be partly due to the changes in oxygen to nitrogen ratio. So we checked these maps like the global ultraviolet maps from this website. And then you can see this was on the third, like you can see like over South Africa and then over Hermanus and also Grahamstown here, like it was normal. But then on the fourth, you can see we start to see a depletion here. And then on the fifth, you can see it has even covered even the some other part in Africa going to the north. So that's where we observed the a big decrease in TEC. And then on the 6th, you see it's starting to recover to go back to normal. So the decrease in TEC values was partially due to the changes in nitrogen ratio. And then in summary, and the TEC over South Africa was studied during a geomagnetic storm of 3 to 8 November 2021. And then a decrease in TEC was observed, as I showed, on the 4th and the 5th of November in both Hermanus and Grahamstown, then which coincided with the depletions on oxygen to nitrogen ratio. And then also the substantial gradients were also observed over the region during the storm period. And then the Hermanus and Grahamstown ionosones were on opposite sides of the gradient on the 5th of November. So that is why you had the smooth curve on Hermanus and the rough curve on Grahamstown. And then also normally in the morning time sector, as I've said, Grahamstown, because it's an east station, you should have higher tech than in Hermanus based on higher solar zenith angle. So thank you very much for your attention.
Okay, so good afternoon, everyone. I'm Adriana Valio from the Center for Radio Astronomy and Astrophysics, Mackenzie. And in case you're wondering, that's in São Paulo, Brazil. So I'm going to tell you today, first of all, I'd also like to thank the organizers for giving me the opportunity to present our work. So I'm going to tell you about 3 solar flares that we observed with a radio telescope. Well, as you all know, the solar flare accelerates particles. Oh, I can read here. Accelerate particles to high energies, producing radiation at all wavelengths of the electromagnetic spectrum, of course. Sorry, of course, including radio. So here are the 3 flares. There were 2 M-class flares. Here are the ghost time profiles, and 1 X flare. And this one was very close to the limb, while these other 2 were closer to the center of the disk. And so here are their characteristics and their times. Oh, and I also want to mention that those 3 flares occurred on the year of 2012. So these flares are from last maximum. And here is the radio telescope that the Center for Radio Astrophysics and Astronomy Mackenzie operates in Argentina, and it's located at the Casleo Observatory. And it operates at 2 millimeter frequencies, 45 and 90 gigahertz with circular polarization. And well, it's one of the flares is very interesting in circular polarization, but we haven't finished analyzing that yet. So sorry, I'm not going to tell you about that. But it continuous operation during the years of 2012, 2013. And it detected 49 events. And we're also currently analyzing all of them. So here is the first flare. And oops, sorry, too fast. And the 45 gigahertz is the red curve here. I want to point out that all 3 flares that we chose to analyze were what we call long duration flares. By long duration, I mean longer than 5 minutes, because most of those 49 flares were just very short bursts, lasting for less than 5 minutes. But these ones lasted for varying from 20 minutes to 2 hours. So this one, so of course, in order to get, so here's the temporal profile. You'll see that all of them have very complex time profile with several peaks. And we chose 4 time intervals here for instants in time to analyze the radio spectra. So here, of course, for that, we had to combine with microwave data from the RSTN. And these are the frequencies from 2 to 15 gigahertz. And these are the spectrum, log flux against log frequency. And you can see the data points here. And the 4 higher frequencies, we fitted using a gyrosynchrotron model, assuming gyrosynchrotron radiation, as you know, is when the accelerated particles, electrons, basically spiral around the magnetic field lines, producing the radio emission at microwaves and millimeter wavelength as well. And in doing this fitting, the Ramati, using this Roven-Ramati code, we are able to probe certain parameters, physical parameters of the imaging source, such as magnetic field, the source size, the total number of accelerated electrons, and the spectral index of the accelerated electron distribution. And so here in the top, in the left panel, you can see the green model is the gyrosynchrotron model that we fitted using MCMC. And here are the parameters: magnetic field, diameter, I'm sorry, I can't really read from here. Total number of accelerated electrons, and this is times 10 to the 33. And then the spectral index. And what I want to point out, which is not common, is that all three flares, as you will see, they have a very hard spectrum with spectral index, the energy distribution of the accelerated electrons. The index going, the average is around 3, but all of them, they have a behavior that it goes from softer spectra and then it gets harder as time evolves. And again, for those of you not familiar with radio spectra, that's not common. So here is the other flare, the June 6th, 2012. And again, you can see very complex structure here in the temporal profile. And again, we chose 4 times periods. And here we also have the 90 gigahertz spectrum, data, which we didn't have. The first one is not that it wasn't observing. The data, the emission didn't get above the uncertainty level. But these 2 ones, we were able to get that emission. And so it's the brown and the red curve. And what you can see here is that the brown curve emission, this is in solar flux units, it's actually higher than the 45 emission. And that's what we're pointing out here. So apparently they have here 2 spectrum components, a second spectrum component, which increases towards higher frequencies. And this was pointed out by Pierre Kaufman in 2004, this terahertz component, using another instrument telescope that we have, that we operate at Casleo, which observes at sub-millimeter frequencies, 212, 405 gigahertz. But we haven't gone and looked for that data yet. And again, we did the same spectral fitting, the gyrosynchrotron fitting. And here, I mean, the same parameters, magnetic field, source sizes, total number of accelerated electrons. And here again, you see the spectral index going from 3 to 2. And then for the last one, again, very complex time profile. This one, you can see here it lasted for 1, 2, 3 hours. So this was a very long duration event with very complex temporal profile. Again, the radio spectrum with the increasing component, also dubbed the terahertz spectral component. And again, the spectral index going from 3 to 2. Usually what happens with the spectral index, it's soft at the beginning, goes hard at the peak of the emission, and then softens again. Again, this is not what we observe on these flares. Okay, so here is just a summary of what I said. The spectra was fit by, the spectra were fit by gyrosynchrotron code. We fitted 4 parameters, and here are the average number of those parameters. And what you can see is that the strongest flare, this is the X flare, the other 2 were M2, M3. This was larger and had a much higher, or twice the number here, or even more, 5 times here, this one, of accelerated electrons. And again, the spectral index, which was very hard, the order of 3, and hardened with time. Okay, coronal mass ejection. So now we went and looked to see if those flares had associated coronal mass ejections. And yes, that's why I'm presenting them here, because they did have. And so here are the 2 M-class events had a partial halo event. Remember, this one was close to the limb. And then the X flare was really a very nice textbook example of a halo flare. And here is the inferred launch velocity and the kinetic energy, which we got from the LASCO catalog. And and of course, you know that the CMEs will cause space weather events, which we just saw here. We just heard of this just before the break. a lot about that, but blackouts, alteration, satellites, orbit, geomagnetic storms, auroras, etc. And so these are the plots of the DST current and the KP index, which we just heard before in the previous talks. And so here is the dashed red vertical line is the launch time of the events, and then using the velocity, the launch velocity inferred from the CMEs, and assuming that they just came in a straight line with a constant velocity, which we know it's an approximation, but we can get an idea of what the arrival time would be at Earth. And so, and that is this vertical dash line. You can see that for the first one event, which happened close to the limb, we don't really see anything. These effects here are from later CMEs that were launched, and which had, because I mean, of course, these CMEs had a coincidence in time of a few minutes with the flare that we measured at radio, with the start of the flare that we measured at radio. But the two other flares, these two other flare-associated CMEs did have effects here. So we do see here the decrease in DST for, of course, the X flare had a much higher, a larger impact. And so in the next slide, I have a table with the numbers. So this one probably missed Earth. It was a high velocity, it had a high velocity, but because it was launched close to the limb, it probably missed our planet. And the other two hit our planet. And of course, the X flare had a larger impact, which had more kinetic energy, which probably more massive, and reached a DST of minus 139 and a KP index of 6. Well, KP is the geomagnetic 3-hourly planetary K index of a storm. And we just saw before a very nice explanation of what those indexes mean and what we call severe storms. So the X flare might be considered a severe storm as far as DST index goes. And there's also a report of an aurora australis recorded by the crew on board the International Space Station on July 15th. And that's 3 days after the last event, the X event. So, oops. So to summarize, we analyzed 3 solar flares detected by the POEMAS. Oh, I forgot to mention the name. I mean, it took me a very long time to figure out this nice acronym, which you might have guessed that it sounds the same in Portuguese. It's the same in English. It means poems. And polarimetric emission of millimeter activity of the sun. And it also works in Portuguese. So that was the tricky part. And all events were accompanied by a coronal mass ejection, either full or partial halo. And of course, the tricky part is always to infer the CME and the space weather here on Earth. But we managed, I think we did manage, though, assuming that, as I said, the velocity of the CME. So the 2 M-class but before I go into that, we model the radio spectra combining millimeter and microwave emission. And we were able to estimate magnetic field's total number of electrons and the spectral index. The important thing here is that from those parameters, the 2M class were more compact, and the source emitting the radio emission had stronger magnetic field than the X flare, which probably came from larger and higher up loops. But all of them had a hard spectral index. The event near the limb was a near miss. We didn't get much effect here on Earth, but the other 2 did hit Earth and cause disturbances on our planet. Nothing major, but it did cause. And of course, the X event, the X flare had an associated CME, which had the hardest impact. And I think that's all. Thank you, and I'll be glad to take questions.
So thank you for the lovely talk.
Thank
My question is to the impact that the various CMEs made when they reach Earth at the L1 point. I see, so you're saying the first one arrived, but it didn't give much impact. So you're assuming that it missed. So I'm curious about how you determine then the arrival time if there's no clear signature on the DST and the other parameters. So how do you determine that that was the arrival time?
Oh, okay. Well, the arrival time is very simple. I get this velocity, which is the launch velocity that you calculate from those height time plots from the LASCO catalog, the CME front. And so you just do the 700 kilometers per second traveling one astronomical unit, and then that will give you the velocity. It's just the one astronomical, the time is the one astronomical unit divided in kilometers divided by the 700. That will give you, oops, sorry. Here, it will give you the travel time in days. Very simple calculation, very simple approximation that they just came in a straight line and they're not decelerated in interplanetary medium, which is an approximation. But the other, those large disturbance here, there were other CMEs that were halo event that came to Earth. And even if you look here, it's, oops, sorry. One more. See, it's not really a halo event. So it didn't probably, well, this one is really a halo event. And this one, you can see that there is a mission all the way here. Okay, thank you.
The final part of this session. Hopefully you're not tired of CMEs. You're about to hear about them in spades, right?
That's correct. So while the slides have been up, let me introduce myself. I'm Bhargav Vaidya, faculty at IIT Indore. And I'm going to present our recent work on understanding the geo-effectiveness of CME-CME interaction. The work that has been led by my PhD student with a collaboration here with Stephen Lotz in SANSA. So basically, when you talk about the CME-CME interaction, there have been many instances of where you have seen that there are multiple CMEs interacting with each other as they propagate within the inner heliosphere. And there have been a lot of discussion about what this CME-CME interaction can impact upon, and they are essentially one of the primary drivers of particle acceleration. So here is a very simple example where you have two CMEs, the pre-CME, which is driving the shock, and the primary CME, which is essentially accelerating the particles. Whereas within this complex structure of merging of magnetic fields, you can have reconnection events, which can actually produce these seed particles to further accelerate these particles to much higher and higher energy. But the bigger question, and this has also been discussed in today's morning talk by Angelos, that the CME propagation has become one of the major kind of the open question in the field of heliospheric studies. And the main question that we want to answer, or at least we want to attempt to answer through simulations, is how do transients evolve and interact with ambient solar wind as they move through the heliosphere, and what impact do they have on the space weather? And that is something which is what I'm going to focus on as part of this particular talk. And to do this, what we have done is we have developed a space weather adaptive simulation framework called SWASTI, which means good luck in Sanskrit. And it essentially is a three-dimensional physics-based MHD model, which kind of is based on an open source code called Pluto. And it is basically driven by an inner boundary condition at 0.1 AU, which is the standard what people use. And it can adopt or use several of the magnetograms like the GONG, HMI, ADAPT magnetograms as well. And to compute, or it basically extrapolate the magnetic field lines from these magnetograms up to 0.1 AU and uses an empirical WSA relation to compute the velocity. And from there on, it basically solves the full set of MHD equation in 3D to compute the plasma parameters at up to 2.1 AU. And This is essentially designed to complement the Aditya L1 in situ data, which will be available pretty soon. And the USP is that it can have some user prescribed cadence and also simultaneous multi-vantage point data. So here is an example of a CR2104, and you can see how well the model can actually represent or manage the solar wind velocity. But since the intention is to understand the CME, we essentially have incorporated two models of CME injection. One is the cone model, which has been well done, and however, it does not incorporate the magnetic fields within the CME flux tubes. But the other one, which we have, is essentially the fried model, which has been developed by Isevin in 2016. And here you can see how the CME or the flux tube is basically injected into this inner boundary, which is represented by the orange circle, and the magnetic fields variation in three components shown here, which are essentially the boundary conditions for our MAG simulations. And the model basically can account for all the different kind of complex CME properties like pancaking, skewness, flattening, and so on and so forth. So here is one particular example or a case study of CR2165 using the SWASTI framework, where we have actually studied how multiple CME interact with each other. And here you can see the density evolution, and this is the Earth, this is the Sun, and you can also see the temperature. And when you plot the properties, the plasma properties at L1, which is blue, is basically using the Omni data, and the red is essentially the from the model. You can see a very nice match, not only for the velocity and density, but also for the BZ. And then what we can do is, using these plasma parameters, you can actually extrapolate using semi-empirical models to compute the DST indices. And this has also been done to kind of showcase that it can very well trigger the DST index storm or the geomagnetic storm, which has also been observed with the data shown in black. So this kind of showcases how one can do a study of a particular event, but that is not enough to understand the propagation at all. So we would like to essentially establish something like an ensemble study, where we want to understand what happens when two CMEs interact as they propagate within the inner heliosphere. So in this aspect, what we have done is we have introduced a realistic solar wind condition, and we have injected two CMEs. The first CME is essentially having a fixed CME parameters or the fixed parameters of density, velocity, magnetic flux, and the tilt. And then for the CME2, we vary the parameters and considered 16 cases where we vary the density lesser than and higher than the fixed CME1 density, and the velocities are always higher than the CME1 densities, and the flux also is lesser and the higher than. And also for the tilt, we change between 0 and 45. And what we do is we study basically the properties of how the CMEs evolve at three different longitudes, that is -10, 0, which is the L1, and +10, which is slightly above L1. And here you can see how what we have done is we have essentially used tracers to identify the structure of the CME. And this is the red part is the first CME, and the green part is the second CME. And this is for the low density case. And this is exactly same time evolution. And you can clearly see the differences that are existing when these two CME interacts, especially because of the fact that you have a fast stream here of the solar wind, which kind of hinders the progress of the first CME, and the high density of the second CME hits the first CME in this particular time frame. When you look at the evolution more closely of these low densities and high density cases, you can see the 4 different cases which have been proposed of how the CME-CME interaction happens. Initially, both the CMEs are essentially moving and coming out, and then the CME actually enters into the sheath of the first CME, and then ultimately it kind of enters into the cloud and the sheath, and then kind of impacts the shock. And this evolution is different for the different input parameters of the CME2, which kind of indicates that by changing the CME2 parameters, you can actually have a completely different impact on the L1 and regions around it. And that is basically what you can do. And so what we have done is we have looked into what impact it has on the CME by doing an estimate of the kinetic energy gain, the momentum gain, and the magnetic energy gain on CME1 because of CME2 for the different cases. So I want to highlight over here, sorry. I want to highlight over here this particular case when you have no tilt. You can see a drastic difference between these cases as well as these cases when there is a change in momentum. And these are really the high density cases. So the high density CME2 is kind of driving much larger change, both in the momentum and the kinetic energy of the first CME, which is kind of showcasing how the dynamic pressure is playing a role for these kind of CMEs. And if you look at the magnetic energy or the change in the magnetic energy, there is significant difference between the high flux and the low flux states of the high density cases. And it kind of showcases how there's a growth initially because of the compression generated by the incoming CME. And then there is a decay in the magnetic fields because of the reconnection that is happening within these CMEs. And it kind of showcases how the magnetic energy is falling down. And similarly with the tilt cases, where we have a relative tilt between the two CMEs, there are similar signatures. However, the changes within these kinetic energy and the momentum are less drastic as compared to the cases where we do not have any tilt and there's a kind of head-on collision in some sense. So this kind of indicates that such kind of ensemble studies provides an idea of what impact the CME1 will have depending on the conditions of CME2. And that is what is there. And also, if you look at the L1 property, when you basically this whole complex structure, which is kind of showcased here in these nice contours, when it kind of encounters L1, you can basically see that there are significant differences in these velocity, density, and BZ at 3 different points. So the orange one is at -10, the green one is +10, and the blue line is essentially just at 0 degrees. So we are recording these 3 longitudes, and we can essentially see how the structure or the in situ properties are different in these 3 longitudes. And it clearly showcases, highlights the importance of doing a much more, rather than doing 1 point observation, rather doing a more kind of stereoscopic observation or a larger 4π kind of observations to capture these kind of processes and further constrain our model. In addition to this, when we are essentially studying this CME-CME interaction, we also saw indications of very nice signatures of reverse shock formation. As you can see over here, this is at a much evolved state in the CME-CME interaction. And you can see over here, this is essentially the density, and you can clearly see this is the velocity, this is the density, and you can see the temperature. You can see how ripples have been formed because of these shock interaction formation of a reverse shock. And this reverse shock shows ripple features in all the quantities. And this is also kind of, since we have kind of this ensemble cases are done such that the interaction happens close to L1, we can see their effects even in the L1 signatures, where these are the forward shocks where the density and everything jumps. So this is essentially the forward shock picture, and this is the reverse shock picture where the velocity jumps, but the density and the magnetic fields kind of drop. So these kind of signatures are also seen here as the forward shock and the reverse shock, and these are kind of recorded here. And recently, Solar Orbiter as well was able to kind of measure the forward and reverse shock in their observations, indicating that there exists that CME-CME interaction produces such kind of reverse shocks. But this observation was done at 0.5 AU, and thereby the signatures coming to L1 were not recorded. However, at 0.5 AU, they could actually see the formation of forward and reverse shocks, which are due to the CME-CME interaction. So the question is that how do these kind of interactions help or do have signatures? Do they have signatures even in the DST index? And we could actually compute the DST index using semi-empirical form. And you can essentially see that there is a significant variation in DST index for these different 16 cases over here. So this is essentially going from low speed, low density, low flux to high speed, high density, high flux. And you can clearly see that the magnitude of the DST index, and these are essentially showcasing the sum, the minimum, and the maximum at 3 different longitudes. There is +10, -10, and 0 longitude. And you can clearly see that there is a drastic difference between when the properties are kind of changed and it kind of significantly changes the DST index. What I also wanted to highlight is these particular cases where you have the high flux here, and these high flux cases have been showing us signatures of reverse shocks, and these reverse shocks, which are basically ripples in these densities and temperatures and velocities, are also kind of reflected in this recovery phase of the DST index, where you essentially have this wiggles coming across and kind of indicating this. But these are essentially for the cases where the interaction happened much closer to L1, and you can actually see the effect of the reverse shocks as such. So finally, to summarize, what we have done is essentially to complement the Aditya L1 in situ data. We have developed a fully operational tested space weather modeling framework. And in this, we have performed ensemble studies highlighting the complex and the non-uniform interaction of CME-CIR, mainly hindered because of these fast stream, slow stream interactions and the CME-CME complex interaction. We also saw that the CME2 properties essentially control the CME1 kinetic energy and the magnetic energy, and can alter essentially the arrival times of the complex ejecta, as you saw how the L1 signatures are changing at different points on these things. And in certain high flux cases, high density and high speed cases, they tend to form reverse shocks. These reverse shocks also have signatures in DST index and also within this thing. But what is essentially required in order to understand and crucially kind of highlight and constrain the model is to get a multi-vantage data point, both with the imager and also at near L1, to kind of not only constrain, but also understand the complexities that is involved here. So in the last, I just want to showcase our preliminary model for the May 2024 kind of events, which kind of clearly also shows how multiple CMEs are injecting, and you can see the effect over there. Thank you so much.
Okay, interesting talk. Have you compared, I mean, I know what you've done, but have you compared with, like, if what would the impact be of just one of those single CMEs? You know, I mean, I know that it will enhance, but, you know, like quantitatively, have you compared, well, if it's just one, the same with the same parameters?
Yes,
what would
yeah.
it be
So
like?
basically, the main idea for this work was CME-CME interaction, but we have in earlier work, which is already published, we focused on one particular CME, and we essentially studied, which I could not show here, the impact of the drag, the solar wind drag, the ambient solar wind drag on the CME as it propagates from point 1 to 1. And we could see that the drag initially is all negative. So essentially, so basically the CME is kind of pushing itself to the solar wind, but as it evolves, the drag kind of equilibrates. So essentially you have positive and negative drag kind of uniformize, and kind of the impact of the CME is kind of much more equilibrated. And as far as the DST index is concerned, yes, you essentially have if it hits you, then you basically have the DST falling down. But I mean, these are just what you can say ensemble studies. But if you want to do actual case studies, you can also kind of do this. And I must point out that for this CR2165, all the CME parameters were derived from GCS fitting of the CMEs, and so we could actually make a good prediction.
Okay, thank you. But what I meant was, like, can you quantify, like, say, well, if it's just a single CME, the impact is 1. But if it's a CME-CME interaction, the impact will be 1.5 to 3 times.
Okay, if we haven't done this, quantified it, but this is definitely possible with the solution. Oh, well, it all depends on the CME parameters, I would say so. No, it does depend on the CME parameters. I mean, you can actually, I mean, if you see this, yeah, I mean, you can see over here how this is multiple CMEs, but you can see how this is kind of changing just based on CME parameters. There's a drastic change over here in this panel. Yeah. Thank you.
Yeah, maybe I missed this. How do you calculate geo effectiveness?
Well,
with your
we
CMEs?
compute the DST indices using the semi-empirical model. So essentially, there's a O'Brien and McFerran model, which kind of computes the from the dynamical pressure and the BZ component. Yeah. Yeah. Thank you.
Yeah, one quick announcement. I just want to remind you that tomorrow morning at 8:30 there will be the plenary talk by Sarah Gibson for our symposium. The talk will be in auditorium 1, which is on the first floor, all the way down this corridor. Okay.